Imagine a world encased in ice. A planet plunged into a deep, cold sleep so profound it's hard for modern humans to comprehend. It was a time of grandeur, unimaginable, even in the wildest dreams. Here, in this pristine silence, the Earth itself seemed to hold its breath, frozen by the great glaciations, when silence stretched for thousands of kilometers in all directions. Imagine a landscape so endless and blindingly white that the very horizon dissolved into this snowy haze. In this deafening silence, history was made. Veritable titans, clad in thick fur, roamed this silent white desert. The tread of gigantic mammoths echoed loudly in the frozen ground, and in the shadows of ice ridges, saber-toothed predators stalked their prey, their fangs deadly weapons, silently pacing the snow. The air here was thick and frosty, imbued with the very essence of ancient wild life. This is a tale of endless winters, of mysterious great migrations across frozen continents. It is a story of creatures that once ruled this planet, now lost forever. And this story still lingers in the air. Today, scientists, uncovering layer after layer of permafrost, are discovering frozen giants. Each discovery is a key to unraveling the mysteries of a bygone era. But what really happened then? There is still no complete answer. And even now, as we watch our own world change, we involuntarily turn our gaze to the past. What other secrets does the ice hold, and what else vanished without a trace as it melted? Let's embark on this exciting journey into prehistory, to the Ice Age. No matter where you are on the globe or what time it is, this story is part of your past, for it shaped the world we live in today. Get ready for a grand tale of how ice slowly but inexorably retreated from our planet. First, what do we call an ice age? It wasn't just a harsh winter, it was a colossal period of time when the climate across the entire Earth was far harsher and colder than we're used to. During this era, vast tracts of land were buried beneath enormous ice sheets we call glaciers. And we're not talking about small ice fields. No, these were mighty, multi-kilometer thick sheets of ice that covered entire continents, stretching for thousands of kilometers. The last such period, which is most often referred to when speaking of the Ice Age, began approximately 110,000 years ago and ended around 12,000 years ago. However, it is crucial to understand, an ice age is not a single event, it is a cyclical process. There was a much longer period in our planet's history when ice caps existed stably at the poles. In fact, even our modern era can be considered only a part of this protracted ice age, which began approximately 2 million years ago. It consists of a series of cold phases, the aforementioned ice ages, and warmer interglacials, one of which we are currently living in. Most of us, of course, picture the last glacial maximum, the most recent episode of this global cooling, which left the most visible scars on the planet. At that time, the ice sheet was truly enormous, covering much of North America, Europe, and parts of Asia. Let's look at North America. Here, the Laurentide ice sheet reigned supreme. It covered virtually all of modern-day Canada and, like a gigantic tongue, slid far south into what is now the United States, reaching states like Illinois and Missouri. Meanwhile, in Europe, the Scandinavian ice sheet spread out. It covered all of Scandinavia, the British Isles, and large swaths of modern-day Germany and Poland. Furthermore, in high-altitude regions around the world, be it the Alps, the Himalayas, or the Andes, their own, albeit smaller, but no less impressive ice caps formed. But even those regions fortunate enough to escape direct ice cover experienced its chilling breath. Temperatures plummeted worldwide, precipitation patterns changed, and sea levels dropped catastrophically. So, what is a glacier? It's more than just a frozen block. It's a living, moving force of nature, a colossal mass of dense ice, compressed over centuries, which, under the pressure of its own colossal weight, begins to slowly but inexorably creep, like an incredibly viscous and dense river. A glacier is born where snow falls for years without having time to melt. Layer by layer, it accumulates, compresses, and turns into crystalline ice. And when the mass reaches a critical point, the ice begins to deform and flow. Glaciers can be found high in the mountains, where they fill valleys, or as endless ice sheets covering entire continents. This is why they are called ice sheets or continental glaciers. An ice sheet is a completely different scale. It's a gigantic glacier covering over 50,000 square kilometers. These truly titanic ice sheets, which defined the Ice Age, were so heavy that their own weight caused them to spread outward from a central dome. Today, only two such giants remain on Earth: the Antarctic and Greenland ice sheets. But during the last glaciation, there were many more. Their incredible size and weight gave them the power to change the very face of the planet. They moved, crushing mountain ranges, gouging out deep valleys, and transporting unimaginable volumes of rock and sediment on their bodies. These icy monsters had a colossal impact on the global climate. With their blindingly white surfaces, they reflected enormous amounts of sunlight back into space, preventing the planet from heating up and maintaining low temperatures. Enormous volumes of water were trapped within them, causing a sharp drop in sea levels. During the last great glaciation, these very same ice sheets dominated the Earth's surface. These weren't just frozen expanses. They were entire continents of ice, several kilometers thick. They radically reshaped the continents as we know them. The most impressive of these were the Laurentide Shield in North America and the Scandinavian Shield in Europe. Their monstrous power gave rise to many modern landscapes. The Laurentide ice sheet originated in the center of what is now eastern Canada, but over time it grew to incredible proportions, covering almost the entire country and extending far west and south, deep into the modern-day United States. At its peak, it reached the Ohio and Missouri rivers. Imagine, the places where cities in Minnesota, Wisconsin, Michigan, and New York now stand were once buried under a thick layer of ice. And what a layer! Scientists estimate that in some areas, especially over Hudson Bay, its height exceeded 3 kilometers. Imagine a mountain range composed entirely of pure ice, slowly moving across the Earth, centimeter by centimeter. The weight of this ice giant was so great that it literally pressed down on the Earth's crust, causing the land beneath it to sink. Even today, thousands of years after the ice melted, some areas of land that were under its weight are still slowly rising. This process is known as isostatic rebound, or, more simply, the straightening of the Earth's crust. This rebound is a silent testimony to the unimaginable pressure this land once endured. As this ice sheet moved, it acted like a giant scraper. It stripped away soil and rock, plucking house-sized boulders from the ground, crushing them into fine powder, and carrying them hundreds of kilometers from their home. This process, called glacial erosion, created a multitude of unique landforms. For example, drumlins, elongated hills that mark the direction of the glacier's movement, or eskers, long, sinuous ridges left behind by rivers that once flowed within or beneath the ice sheet. The Great Lakes of North America are a direct legacy of the destructive power of the Laurentide Shield, which gouged out deep basins that later filled with meltwater. In Europe, the Scandinavian ice sheet was no less massive. Originating in the mountains of Scandinavia, it spread far beyond their borders, covering Norway, Sweden, and Finland, before crossing the Baltic Sea and encroaching on what is now Germany, Poland, and Russia. Furthermore, its icy shell covered virtually the entire British Isles, with the exception of just a few of the highest peaks. Like its North American counterpart, the Scandinavian Shield reached a thickness of thousands of meters in its central parts. Its movement formed the famous fjords of the Norwegian coast, deep, narrow sea inlets that are essentially flooded glacial valleys. The glaciers also left behind vast plains covered with so-called moraine, a mixture of clay, sand, gravel, and boulders dragged beneath the ice. These glacial deposits later became the basis for the fertile soils in many agricultural regions of Europe. But the influence of these ice giants wasn't limited to the lands they covered. Their very presence radically altered the global climate. They altered the usual patterns of winds and ocean currents, and at their edges, they created vast periglacial zones. These harsh territories experienced brutal freeze-thaw cycles. These zones were renowned for their permafrost, permanently frozen ground, and unique landscapes such as frost mounds or pingos and patterned polygonal soils. The enormous amount of water locked within these ice sheets caused sea levels to drop by as much as 120 meters. This exposed vast tracts of continental shelf and created land bridges between continents. The most famous of these is the Bering Land Bridge, which connected Asia and North America. These icy worlds were not static. They were dynamic landscapes that were constantly changing. The ice advanced and retreated, leaving an indelible scar on the face of the Earth and forever altering the course of life's evolution. Climate. During the Ice Age, weather conditions across the planet were radically different from what we're used to. The most obvious and primary difference is, of course, the much lower average temperature. According to modern estimates, globally, the planet was approximately 8 to 10 degrees Celsius colder. While the difference may not seem like much at first glance, it had profound consequences for all of Earth's climate systems. The climate of those times was extremely unstable and contrasting. Particularly harsh conditions prevailed at high latitudes, near the poles, and at the edges of massive ice sheets. However, it became colder everywhere, with even tropical regions experiencing temperatures noticeably lower than today. Long periods of severe cold alternated with short, slightly warmer intervals, but the overall trend was inexorable. The planet was freezing. And it wasn't just the temperature. The harsh conditions of the Ice Age in Africa were caused not so much by the advance of the ice itself as by its consequences: catastrophic water shortages, constantly changing landscapes, and colossal environmental pressures. These factors became the crucible in which the foundations for the future development and global triumph of modern humanity were forged. It was an era of extreme environmental instability, which, paradoxically, served as a powerful stimulus for human innovation and adaptability. Let's fast forward to the darkest and coldest act of this glacial drama. The last glacial maximum, which scientists call the LGM for short, represents the harshest and most protracted period of glaciation during the last Ice Age. This phase of unimaginable cold began approximately 20,000 years ago. It was then that gigantic ice sheets reached their maximum size, spreading across the continents and radically reshaping not only the Earth's surface, but also its climate. To truly grasp the scale of those events, we need to understand the conditions the planet experienced during the last glacial maximum. This is key to understanding how dramatically our world can change and how those changes impact all life. Consider the Northern Hemisphere. It was dominated by enormous continental ice sheets. In North America, for example, the Laurentide ice sheet, like a gigantic blanket, covered almost all of modern-day Canada and extended deep into the United States, reaching as far as the Ohio and Missouri River valleys. Its thickness was simply monstrous. Estimates suggest it exceeded 2 kilometers in central regions, such as Hudson Bay. The weight of this ice mass was so enormous that it literally pressed the Earth's crust hundreds of meters deep, creating incredible deformations on the surface. This effect, like a slow exhalation of the planet, is gradually disappearing, and the land in those regions continues to rise to this day. Now, let's look at Europe. Here, the Scandinavian ice sheet covered virtually all of Scandinavia and the British Isles, with its icy tongues reaching into the heart of Central Europe. But don't think of these ice sheets as motionless boulders. No, they had a life of their own. They flowed slowly under their own weight, like frozen rivers, grinding rock into dust, transporting enormous volumes of sediment and carving into the planet the characteristic glacial scars we see today: drumlins, elongated eskers, and deep basins that became the Great Lakes. And that's not all. Far from these major ice caps, in mountain ranges like the Alps, Himalayas, and Rockies, mountain glaciers have also expanded significantly, becoming true ice caps. All this ice is water extracted from the world's oceans. The enormous volume of water locked in these ice sheets led to a sharp, dramatic drop in sea level. At the peak of the last glacial maximum, sea levels were approximately 120 meters lower, the height of a 40-story building, than they are today. This collapse exposed vast tracts of the continental shelf, creating new landmasses and land bridges connecting the continents, which became a crucial factor in the spread of life across the planet. The most striking and well-known example is, of course, Beringia, a vast land bridge that linked Asia and North America. It was along this land bridge that the migration routes of ancient animals and our distant ancestors ran. But there were others as well. A vast territory called Sunderland emerged in Southeast Asia, and the land known as Doggerland spread out in the place of the North Sea. All of this radically impacted the spread of life on Earth. Global temperatures during that period were significantly colder than we can imagine. On average, the Earth's surface was 8 to 10 degrees Celsius colder, and this cooling was uneven. It was most noticeable, of course, at high latitudes near the giant ice sheets. But even in tropical regions, much cooler conditions prevailed. This icy cold was greatly amplified by the high albedo, that is, the reflectivity, of the vast ice and snow cover. Imagine a giant mirror the size of a continent. A significant portion of the sunlight was simply reflected off this white surface back into space, further cooling the planet, preventing it from warming up. This harsh climate caused profound fundamental changes in the plant world. Forests, as we know them, virtually disappeared from high latitudes and elevations. In their place were vast, treeless expanses. These were dominated by tundra and the so-called mammoth steppe, incredibly productive, albeit cold, grasslands that covered much of Eurasia and Beringia. And on these frigid grasslands, countless herds of Ice Age megafauna grazed: giant woolly mammoths, mighty woolly rhinoceroses, and enormous steppe bison. In areas adjacent to ice sheets, periglacial conditions prevailed. This meant permafrost, permanently frozen ground that prevented plant roots from penetrating deeply. This, in turn, led to the development of unique soil features, such as patterned soils and icy pingos. Deserts also expanded their reach in many parts of the world due to the significantly drier climate. Atmospheric conditions were also extreme. Climates around the world dried as far less moisture evaporated from the cold oceans. This led to reduced precipitation in many regions, causing ancient lakes to shrink and dry out, while deserts advanced. Strong, incessant winds were common, driven by the enormous temperature differences between the icy land masses and the relatively warm oceans. These winds lifted and transported clouds of fine sediment known as loess over vast distances. The winds carried fertile silt, which settled hundreds of kilometers away from the glaciers, eventually creating incredibly fertile plains. For example, the famous Loess Plateau in China and the fertile lands of central North America are all legacies of these ancient winds. The atmosphere at that time also contained fewer greenhouse gases, primarily carbon dioxide and methane. The planetary blanket was thinner, contributing to lower temperatures by weakening the greenhouse effect. Data from ice cores in Antarctica and Greenland provide direct, irrefutable evidence of this. Air bubbles trapped in ice tens of thousands of years ago contained significantly lower concentrations of greenhouse gases. The extreme conditions of the last glacial maximum exerted colossal pressure on all life forms. This was a brutal natural selection process. Animals adapted by growing thick fur, increasing in size, and developing complex migratory behavior. Human populations, including early modern humans and our Neanderthal cousins, demonstrated remarkable resilience and ingenuity. They developed new technologies, created specialized tools, refined hunting strategies, and built more reliable shelters. All of this was absolutely essential for survival in the inhuman conditions of the glacial world. The human ability to adapt to such extreme conditions demonstrates our unique, unparalleled adaptability. But the last glacial maximum was not a static period frozen in time. It actively shaped the Earth's physical geography, its ecosystems, and the very course of human history. Its severity underscores the powerful natural forces that drive long-term climate change on our planet. Earth's climate is influenced by a multitude of factors, some of which operate over tens, even hundreds of thousands of years. One of the most significant are the natural cycles of changes in our planet's orbit and axial tilt, known as the Milankovitch cycles. These cycles describe predictable long-term variations in the Earth's motion around the Sun, which in turn influence the climate. Today, scientists agree that these celestial cycles are the master controllers governing the alternation of ice ages and warm interglacials. However, our planet's motion around the Sun plays a significant role not only in the onset of great glaciations, but also in how solar heat is distributed across different parts of the globe. There are three main Milankovitch cycles that have a decisive influence on Earth's climate: eccentricity, axial tilt, and precession. Each of these cycles has its own duration and influences the amount of solar energy our planet receives at different latitudes and times of year. Eccentricity is, simply put, the shape of Earth's orbit around the Sun. This orbit is not a perfect circle, but an ellipse. The eccentricity cycle describes how elongated or circular this orbit becomes over time. This cycle has a primary period of about 100,000 years and a secondary period of 400,000 years. As the orbit becomes more elongated or elliptical, the distance between Earth and the Sun changes significantly throughout the year. This means that the difference in the amount of solar energy received at perihelion, the point when Earth is closest to the Sun, and at aphelion, when it is farthest away, becomes greater. However, the total amount of solar energy received over the year changes only slightly. What does change, however, is the length and intensity of the seasons. For example, if Earth is closest to the Sun during the Northern Hemisphere summer, that summer will be shorter but hotter. Secondly, the tilt of the Earth's axis. This describes the angle at which the Earth's rotational axis is tilted relative to the plane of its orbit. Currently, this tilt is approximately 23.5 degrees, but it is not constant, fluctuating between 22.1 and 24.5 degrees. A complete cycle of these oscillations takes approximately 41,000 years. It is this tilt that determines the change of seasons on Earth. The greater the tilt, the more extreme the seasons become. Summers are hotter and winters are colder. However, for the formation of giant glaciers, cool, mild summers are more important than harsh winters. If summer temperatures are not high enough to completely melt the snow and ice accumulated during the previous winter, they begin to accumulate year after year, layer by layer, and glaciers form as a result. Thus, it is the decreasing tilt of the axis that promotes milder summers at high latitudes, which, as a rule, initiates the process of ice sheet growth. And finally, the third phenomenon is precession. This is the movement of the Earth's axis of rotation, similar to the oscillation of a spinning top. This oscillation slowly changes the direction in which the Earth's axis points in space. This precessional cycle consists of two main components with different periods. Imagine a grand cosmic mechanism, a universal clock whose hands move in increments of tens of thousands of years. Our planet, Earth, is part of this mechanism, and its movements determine great climatic epochs. The oscillations of the Earth's axis, a kind of slow rocking of the planet, occur with a periodicity of approximately 19,000 to 23,000 years. It is this celestial dance that dictates the seasons on our planet. Seasonality is directly dependent on the point at which Earth finds itself in its elongated elliptical orbit. Let's look at our modern era. Right now, summer in the Northern Hemisphere occurs when our planet passes the point of its orbit farthest from the Sun, the so-called aphelion. This factor makes our climate comparatively moderate. But let's fast forward 11,000 years into the past. During the previous cycle, things were different. Summer occurred when Earth, on the contrary, approached the Sun at its closest point, the perihelion point, and this, of course, made the climate much hotter. The complex interaction between the shape of the orbit and the wobble of the planet's axis, known as the precession of the equinoxes, determines the fundamental question of which hemisphere will receive the most solar heat, and herein lies the key to the great glaciations. It is precisely the cool, mild summers in northern latitudes that become the key to glacier advance. Such summers prevent the snow and ice that fell during the long winter from melting, allowing it to accumulate year after year, layer after layer. Thus, it is this great trinity of cosmic rhythms, working in unison, that writes the Earth's climatic history over millennia. The amount of solar energy received by different parts of our planet at different times of the year varies enormously. Although the overall heat flux from the Sun remains virtually constant, its distribution across the Earth's surface is constantly changing. These changes are particularly pronounced in the high northern latitudes during the summer. It is these fluctuations that trigger the onset, or conversely, the end of ice ages. The Northern Hemisphere plays a central role in this drama. The reason is simple. It is home to gigantic land masses that could serve as a springboard for the advance of icy armies. If the northern continents receive less solar energy during the summer months, the chances of winter snows completely disappearing drop sharply. This paves the way for snow to accumulate over many years, which, under its own weight, compresses, turning into glacier ice and forming gigantic glaciers. As soon as these ice sheets are born, they begin to change the climate, setting off a powerful chain reaction. Their dazzling white surface, with its high albedo, acts like a giant mirror. It reflects the lion's share of sunlight back into space, preventing it from heating the planet. As a result, the Earth cools even more, and the ice cover continues to grow. The theory describing these cycles, named after the Serbian scientist Milutin Milankovic, brilliantly explains the periodic advances and retreats of glaciers in the past. Its validity is supported by geological records, such as sediment cores from the deep ocean and ice cores extracted from the Antarctic and Greenland ice sheets. Of course, other forces also influence climate: volcanic eruptions, greenhouse gas concentrations, and continental movement. But Milankovic's theory remains the primary tool for understanding the great climatic swings of the past. These cosmic cycles serve as the conductor that orchestrates the ice ages, providing a predictable astronomical framework for deciphering the climatic history of our planet. A key aspect in understanding these global processes is the relationship between the Sun's energy and Earth's ice caps. It's not that our Sun suddenly becomes weaker or brighter. No, it's how the Earth itself captures and redistributes this energy across its surface. Subtle but critical changes in the Sun's orbit, known as Milankovitch cycles, have a dramatic impact on the birth and death of giant ice sheets. The amount of solar radiation, or insolation, our planet receives is the primary factor determining the fate of its ice sheets. Sunlight reaches different parts of the Earth at different angles and at different times of the year. For glaciers to grow, one simple but rigorous condition must be met. More snow must fall during the winter than can melt during the summer. If summer temperatures are too high, the entire snow cover accumulated during the winter will disappear without a trace, and the accumulation process will have to start from scratch. But if the summer is cool enough for at least some of the snow and ice to survive the melting season, a powerful process is triggered. The following year, a new layer of snow will fall on top of this remnant, compacting it under its own weight and eventually turning into a mighty ice sheet. This process is most effective at high latitudes, especially in the northern hemisphere, where vast continental expanses serve as the ideal foundation for the construction of ice sheets. And it is the amount of sunlight reaching these regions in summer that plays a decisive role here. And this process, as we already know, is governed by Milankovitch cycles. Let us take a closer look at each of these cosmic rhythms. First, there's eccentricity, the degree of elongation of Earth's orbit. Imagine Earth's orbit not as a perfect circle, but as a slightly elongated ellipse. Over cycles lasting about 100,000 years, this ellipse alternates between becoming almost circular and then becoming more elongated again. Although the total annual energy input from Earth remains relatively constant, a more elongated orbit exaggerates the difference between its closest point to the Sun, perihelion, and its farthest point, aphelion. If summer in the northern hemisphere occurs when Earth is closest to the Sun, it will be hot. If it occurs at the farthest point in the orbit, it will be cool. It's precisely these cool summers that create ideal conditions for glacier growth, as they dramatically reduce melting rates. Secondly, there's the tilt of the Earth's axis. Our planet, as it rotates, doesn't stand perfectly still in space. Its axis is tilted, and this angle varies between 22.1 and 24.5 degrees in a cycle of approximately 41,000 years. This tilt directly influences the contrast between the seasons. The greater the tilt, the more extreme the seasons become. Summers become unbearably hot, and winters become freezing. Conversely, a smaller tilt results in a milder climate. Summers become cooler, and winters become warmer. A smaller tilt is a real boon for ice advance. High latitudes receive less direct sunlight in the summer, which leads to less intense heating and, consequently, less snowmelt. This allows the snow cover to survive the summer and initiate the process of glacier growth. And finally, the third factor is precession, or the cyclical wobble of the Earth's axis. Like a spinning top, the Earth's axis slowly traces a cone in space. This cycle takes between 19,000 and 23,000 years and determines which seasons Earth will pass through the closest and furthest points of its orbit. As we've already discussed, today the northern hemisphere experiences summer at its farthest point from the Sun, making it relatively mild. But 11,000 years ago, the opposite was true. Summer occurred at perihelion, the point closest to the Sun, leading to a hotter climate. Cool summers in northern latitudes are vital for ice sheets. Ideal conditions are created when the cool summer caused by precession coincides with the maximum eccentricity of the orbit. But the true climate catastrophe that gives rise to ice ages occurs when all these orbital factors coincide, when the cycles align, creating a perfect storm. Minimal solar radiation in the northern hemisphere summer is the recipe for ice advance. Snow and ice persist year after year, accumulating and turning into kilometers-thick ice sheets that spread, engulfing entire continents. Once again, the positive feedback mechanism comes into play. Vast white fields of ice and snow reflect most of the sunlight back into space. This further cools the planet, spurring further ice growth. Furthermore, giant glaciers alter atmospheric circulation and ocean currents, further exacerbating the cooling. The reverse process also exists. When orbital cycles shift, bringing more summer heat to northern latitudes, existing ice sheets begin to melt. If the rate of melting exceeds the rate of snow accumulation, the glaciers retreat. A feedback loop operates here too. Melting ice exposes dark land or ocean surfaces, which begin to greedily absorb solar heat. This leads to further warming and accelerates melting. It is these subtle, slow changes in the Earth's dance around the Sun that explain the grand rhythm of glacial and interglacial periods we observe in the planet's geological record over the past millions of years. Minor, long-term shifts in the Earth's rotation and orbital motion prove to be the primary external factor driving the dramatic fluctuations between periods of all-consuming ice and periods of warmth. Imagine a world locked in ice. A planet in the grip of an ice age did not shed its shackles overnight. The great transition from permafrost to the warmth we know today was not like the flick of a switch. It was a slow, almost imperceptible process of awakening. It all began with the first, almost inaudible whispers of impending changes in the grand mechanism of Earth's climate. These quiet signals, initially unnoticeable against the icy silence, were harbingers of a colossal restructuring of the entire planet. They heralded the coming melting of impenetrable ice citadels, which would forever alter the face of the continents and redraw the map of life on Earth. And the trigger for these titanic processes were invisible forces, subtle changes in the cosmic dance of our planet, celestial mechanics, namely fluctuations in Earth's orbit and axial tilt began to distribute solar heat across the surface in a new way, especially in key northern latitudes. One of the first and most obvious echoes of this cosmic influence was a subtle but steady rise in average temperatures worldwide. During the last glacial maximum, the planet was a truly harsh place. Global temperatures were 8 to 10 degrees Celsius lower than what we're used to. But the slow retreat from this frigid realm began long before its effects became apparent. We have astonishing evidence of this process, veritable chronicles of the past, extracted from the depths of Greenland and Antarctica. We're talking about ice cores, pillars of ancient ice that serve as a time capsule. Analysis of these cores shows that the atmosphere began warming approximately 20,000 years ago, and some evidence suggests this process may have begun even earlier. Each layer of this ice is a page in Earth's climatic history. The ratios of oxygen isotopes locked within the ice crystals directly tell us the temperature that reigned on the planet at any given moment. And these icy chronicles unmistakably point to the beginning of the Great Warming. However, this warming was not uniform. The Earth heated up like a giant furnace, with some areas heating up faster than others. Some regions experienced the warming more rapidly and intensely, especially at high latitudes, where giant ice sheets exerted a dominant influence on the climate. Another crucial sign of impending change was a shift in the very air the planet breathed. The atmosphere began to become saturated with greenhouse gases. Data extracted from those same ice cores, like irrefutable evidence, proves that the concentration of carbon dioxide and methane, two powerful catalysts for global warming, began to rise almost simultaneously with the rise in global temperatures. Imagine, at the height of the Ice Age, atmospheric carbon dioxide levels were extremely low, only about 180 parts per million. By comparison, before the Industrial Revolution, this figure was already 280 parts per million. As the Earth slowly began to thaw, nature itself triggered mechanisms that accelerated the process. Warming oceans, like giant soda cans, began releasing dissolved carbon dioxide into the atmosphere. Shifting ocean currents also played a role, bringing carbon-rich waters from the depths to the surface. At the same time, methane concentrations also increased. Scientists attribute this to the fact that retreating glaciers exposed vast areas that quickly turned into wetlands, ideal methane factories. Furthermore, thawing permafrost released enormous volumes of organic matter, which, as it decomposed, also released this gas. Thus, a powerful chain reaction, a positive feedback loop, was created. Cosmic cycles provided the initial impetus for warming, and the awakening planet itself began to emit more and more greenhouse gases into the atmosphere, which, in turn, heated it up even more. Traces of these changes could also be seen in the plant world. As the climate became milder, especially at the edges of glaciers and in the vast tundra steppes, the plant world began to transform. Armies of cold, hardy species slowly retreated north, giving way to plants that preferred more comfortable conditions. By analyzing ancient pollen preserved in the bottom sediments of lakes and swamps, paleobotanists see this picture in exquisite detail. They observe how the grasses and sedges, characteristic of the tundra, were replaced first by shrubs and then by the first pioneer trees, hardy birches and pines. They required more warmth than the tundra plants, but they were ready to conquer new lands. This botanical march was slow, spread out over millennia, but it was irrefutable evidence that the climate was changing, becoming warmer and wetter, creating conditions for the emergence of more complex and diverse forest ecosystems. The ocean also holds its secrets. Sediments on the seafloor serve as another early indicator of global warming. By studying microscopic fossils, such as the shells of tiny marine organisms, we can reconstruct past temperatures and currents with astonishing accuracy. We see how colossal flows of meltwater from retreating glaciers rushed into the North Atlantic. This influx of fresh water significantly affected ocean circulation, which, in turn, could have led to even more dramatic warming in certain regions. Deep-sea currents, those global conveyor belts that transport heat across the planet, began to reorganize, adapting to the new conditions, thereby contributing to overall warming. And, of course, the most important sign was the retreat of the ice itself. These changes may have been barely noticeable to the ancient hunters of that era, but they were inexorable. With each passing year, summers grew slightly warmer, and less of the winter's snow survived the melt season at the margins of the giant ice sheets and in mountain glaciers. This led to a slow but steady thinning and retreat of the ice fields, which eventually escalated into a massive melt. In the earliest stages of this process, meltwater streams running off the glacial fronts grew ever more full-flowing. This water formed enormous periglacial lakes or altered river courses, causing them to overflow their banks. These first, barely noticeable shifts in the planet's ice balance were a direct response to the slight but steady increase in solar heat reaching northern latitudes. It was a signal from space, heralding the end of a long, icy night. The planet was slowly but surely awakening from the deep cold. The end of the Ice Age, which began approximately 19,000 years ago, was marked by an event of planetary scale, the rapid melting of the colossal ice sheets and mountain glaciers that covered vast swaths of the continents. This process, which scientists call deglaciation, was a true revolution. It radically reshaped landscapes, gave birth to new river and lake systems, and, in essence, created the world we live in today. Initially, the ice retreated slowly, but as temperatures continued to rise, the melting became an unstoppable avalanche. The central stage of this drama was the retreat of the giant continental ice sheets, the Laurentide in North America and the Scandinavian in Europe. Global warming, driven by orbital cycles and rising greenhouse gas concentrations, upset the delicate balance that had existed for millennia. The climate was changing, and the balance between snow accumulation in winter and its melting in summer shifted. Summers became so warm that they melted far more ice than had accumulated during the previous winter. This led to a net loss of ice mass, and the giant sheets began to shrink. They weren't simply melting in place, their edges were inexorably retreating into the continents. Although this process was occasionally interrupted by brief periods of cooling, when the glaciers might even advance slightly, the overall trend was clear. The ice was retreating. As the ice sheets retreated, they left behind a completely new, scarred landscape. The unimaginable mass of ice, moving for millennia, scoured and ground rock, carving out wide valleys, mountain cirques, and deep fjords. When the ice melted, it released the enormous quantities of rock, sand, and clay it carried. This material remained on the surface as bizarre landforms. Morainic ridges, walls of unsorted glacial sediment, mark the boundaries where the glacier's edge once stopped. Elongated hills, known as drumlins, also serve as silent witnesses to this process. Vast expanses of sand and gravel were created by powerful meltwater flows rushing from the glacial front, forming entire scoured plains. These deposits completely reshaped entire regions that had previously been hidden beneath kilometers of ice. One of the most dramatic consequences of glacial retreat was the creation of thousands of new lakes. Meltwater accumulated in enormous quantities, filling depressions carved out by the ice or lingering near ice dams. These periglacial lakes often reached monstrous sizes, dwarfing many modern lakes. A striking example is Glacial Lake Agassiz. This gigantic body of water covered parts of the modern-day Canadian provinces of Manitoba, Saskatchewan, and Ontario, as well as the U.S. state of North Dakota. At its peak, Lake Agassiz was larger than all of North America's Great Lakes combined. These lakes were essentially temporary reservoirs. Meltwater accumulated within them, and if the ice dam holding back this mass of water suddenly broke, it would lead to catastrophic floods of biblical proportions. The retreat of the ice giants became a force that completely reshaped the waterways of entire continents. Imagine ancient rivers flowing along their channels for millennia. Now imagine a kilometer-high wall of ice advancing on them, erasing them from the face of the Earth like a pencil sketch. As the ice began its great retreat, an entirely new world was born from beneath it. Streams of meltwater, turbid and heavy with an incredible amount of sand and rocks, carved new paths for themselves. These turbulent rivers, meandering, rushed away from the ice fronts, carving fresh channels in the earth and forming gigantic plains that we today call alluvial plains. Much of the modern river network in regions that were once icebound owes its origins to these ancient streams. Take, for example, the mighty Mississippi River. Its modern course and all its power are a direct legacy of the meltwater of the gigantic Laurentide ice sheet. It was this ice sheet that fed it, channeling colossal volumes of water and sediment southward. The release of such a mass of water from its icy confines sometimes led to consequences of truly catastrophic proportions. These changes in river flows, their direction, and their strength created the hydrological picture we observe to this day. However, it's not fair to think that warming has been a smooth and straightforward process. Our planet's history is full of sharp and dramatic reversals. Let's fast forward to about 13,000 years ago, to a period scientists call the Younger Dryas. This was a sudden and brutal return of winter that lasted over 1,000 years. In just a few decades, temperatures in the northern hemisphere plummeted to near glacial levels. The Great Melt halted, and, in many places, glaciers began advancing again. This millennia-long cold rematch vividly demonstrates how fragile and unpredictable Earth's climate system was during that era of change. But the eternal cold couldn't hold its ground. After this brief, by geological standards, lull, the pendulum swung back. The warming trend resumed with renewed vigor, triggering the final and most rapid melting of the remaining ice citadels. The scale of this process is simply staggering. In North America, the Laurentide ice sheet, a colossus that covered much of the continent, literally evaporated in a few thousand years, the blink of an eye on the planet's clock. Just 10,000 years ago it was enormous, but by 7,000 years ago only pitiful remnants remained. In Europe, its sister ice sheet, the Scandinavian ice sheet, suffered the same fate. Its melting gave us the unique landscapes of Scandinavia and the British Isles, indented by fjords and lakes. Around the world, mountain glaciers retreated, pouring their waters into the oceans and forever changing the climate of the highlands. Thus, the Great Melt became a geological force of incredible power. It not only raised sea levels, but also left scars and gifts on the face of the planet that defined our world. Fertile soils, thousands of freshwater lakes, new full-flowing rivers, all these are the legacy of the Ice Age, which allowed the modern temperate climate to flourish, where humanity was able to build its civilization. One of the most threatening and tangible consequences of global warming has been the inexorable rise in sea levels. Imagine the scene: waters rising not by centimeters per year, but by meters per century. This phenomenon has completely redrawn the coastlines of every continent, inundating vast territories that were once thriving land. For ecosystems and early human populations, this was a true catastrophe. The scale of this global flood was truly biblical, surpassing anything humankind had ever seen, and it forever changed the geography of our planet. Let's go back more than 20,000 years ago to the height of the last glacial maximum. Looking at Earth from space, we would see a completely different picture. Sea levels back then were 100, and by some estimates 120 meters lower than they are today. That's the height of a 40-story skyscraper. This was due to trillions of tons of water trapped in the ice sheets covering North America and Eurasia. To put this into perspective, if all the remaining glaciers on the planet were to melt today, sea levels would rise by approximately 66 meters. This underscores the colossal amount of water removed from the world's oceans. And then, about 19,000 years ago, the planet began to warm. The ice sheets, those gigantic reservoirs of fresh water, began to melt. Streams turned into rivers, and rivers into raging torrents that rushed from the continents straight into the ocean, causing its level to rise. But this process wasn't smooth and gradual. It occurred in spurts, pulses, sometimes with astonishing speed. There were periods when the ice sheets disintegrated especially quickly. One such dramatic event is known as Meltwater Pulse 1A, which occurred about 14,500 years ago. Just imagine, in just 500 years, global sea levels rose by 20 meters. That's roughly 65 feet. The rate was so rapid that the changes would have been noticeable within a single generation. Coastal dwellers would have seen the sea encroach on their homes and hunting grounds year after year. The most obvious and tragic consequence of this sea advance was the flooding of coastal plains and continental shelves. During the Ice Age, these shelves were not seabed, but vast, dry lands extending hundreds of kilometers from today's shores. These lands were incredibly rich in resources. Herds of mammoths and bison grazed here, unique ecosystems flourished here, and ancient humans found a home and a living here. But as the ocean rose, these fertile lowlands sank one after another. The great hunting savanna, coastal settlements, entire worlds that had fed people for millennia were irrevocably swallowed by the advancing waves. Today, these lands lie at the seabed, making exploration incredibly difficult, but the few discoveries that have been made suggest that life once teemed there. Rising sea levels also altered the very connections between the continents. Land bridges, those ancient highways for the migration of animals and people, were submerged. The Great Bering Land Bridge, connecting Asia and North America, slowly sank beneath the waves until, around 11,000 years ago, it finally closed this vital corridor. A similar fate befell Sundaland, the landmass that linked mainland Southeast Asia with the islands of Indonesia. Its submergence isolated numerous populations, both animals and people, on the newly formed islands. And in Europe, Doggerland, a vast lowland connecting Britain to the continent, was flooded. In its place, the English Channel formed, forever separating the British Isles. These floods didn't just change the map of the world, they set evolution and human history on an entirely new path. For coastal communities of the time, this was a relentless crisis. People whose livelihoods depended entirely on the bountiful bounty of the sea and river estuaries were forced into constant retreat, abandoning their homes and moving ever further inland. Imagine constantly fleeing the advancing waters, generation after generation. This created enormous pressure on social structures and required constant adaptation. And although retreating glaciers opened up new lands in the north, the loss of these rich coastal zones was irreparable. Beyond direct flooding, rising seas also dramatically altered ecosystems themselves. River mouths, the natural nurseries for numerous marine species, were forced to move inland. Saltwater infiltrated coastal freshwater supplies, poisoning sources vital to humans and animals. The entire coastal environment and the resources it offered were completely restructured. The transition from the glacial minimum to the current sea level took between 12,000 and 15,000 years. On average, the water level rose at a rate of about 1 meter per century. But, as we have already seen, this natural process was full of dramatic surges and periods of much more rapid water advances. This glimpse into the past provides invaluable context for understanding what humanity may face in the future, and highlights how powerful and irreversible the impacts of global climate change could be. Our planet's climate system is a complex and dynamic mechanism, and the melting process of glaciers hasn't always resembled the slow melting of an ice cube. In many parts of the world, it has led to the formation of gigantic lakes, imprisoned by natural dams of ice and rock. When these ice barriers couldn't withstand the colossal water pressure, they would break through. Then, freshwater streams of such power were released, the likes of which the world has never seen before or since. In a matter of days, even hours, these megafloods swept across the land, reshaping landscapes with the fury of an awakened titan. These weren't just floods, they were geological cataclysms. They were so powerful that they carved deep canyons in basalt rock, carried house-sized boulders for tens of kilometers, and forever altered the courses of mighty rivers. The most famous and best-studied example of such events are the Missoula floods, which repeatedly swept across northwestern North America. These catastrophes occurred between 15,000 and 13,000 years ago. The source of this destructive force was a gigantic proglacial lake named Lake Missoula. This enormous body of water formed as a result of... Let's travel back in time to an era when the world was just emerging from the icy grip of the Great Ice Age. Here, in what is now western Montana, a truly planetary-scale drama unfolded, born of the melting of the gigantic Cordilleran ice sheet. Imagine a colossal wall of ice, a glacier tongue sliding south, completely blocking the Clark Fork River Valley. It wasn't just a plug of ice, it was a dam created by nature itself over 600 meters high, the equivalent of 2 Empire State Buildings stacked on top of each other, and tens of kilometers wide. This implacable ice barrier completely blocked the river's natural route to the ocean. The water had nowhere to go, and so it began to rise. Day after day, year after year, the water level rose ever higher, flooding valleys and gorges. Thus was born glacial Lake Missoula. At its peak, it was a true freshwater sea. Its basin contained over 2,000 cubic kilometers of water, a colossal volume comparable to half the size of today's Lake Michigan. The water's surface stretched over an area of almost 8,000 square kilometers, and in some places, the depth exceeded 600 meters. But this gigantic ice dam, holding back the lake's unimaginable power, was doomed. It wasn't a monolith of stone. It was ice, living and unstable. The incredible pressure of the water masses pressed against it from within. The water, seeping into the tiniest cracks, acted like a wedge. As it froze, it expanded, tearing apart the ice mass from within. This process, known as hydraulic fracturing, slowly but surely eroded the dam's strength. And then, one day, the fateful moment arrived. The network of cracks grew, and the dam gave way. What followed was apocalyptic. The colossal ice wall collapsed, unleashing the full pent-up power of Lake Missoula. Within days, the gigantic lake was empty. A wall of water, rushing at nearly 100 kilometers per hour, swept across the eastern part of modern-day Washington, rushing through the Columbia River Gorge toward the Pacific Ocean. The volume of this torrent was unimaginable. By the most conservative estimates, it was 10 times greater than the combined flow of all the rivers on the planet today. It was the equivalent of 100 Amazon rivers merging into a single monstrous torrent. The unstoppable force of this water forever changed the face of the Earth, creating a unique landscape known as the channelized barrens. A surreal scene unfolds before us. Deep, winding canyons, dry riverbeds, gigantic basins, and dried-up waterfalls that were once taller than Niagara Falls. But the most striking evidence of this catastrophe is the gigantic ripple marks on the ground. Imagine waves as tall as 5-story buildings, frozen in stone, with crests hundreds of meters apart. This is visible evidence of the incredible power of this ancient flood. The water tore away vast layers of soil and bedrock, revealing the dark basalt cliffs beneath. The stream left other traces behind. Giant boulders, weighing hundreds of tons, were torn from their native rocks, transported hundreds of kilometers, and dropped across the plains like pebbles. This speaks to the colossal carrying capacity of the water, which played with these boulders like toys. And the most terrifying thing is that the Lake Missoula flood was not a unique event. Geological evidence tells an even more terrifying story. The ice dam rebuilt and burst again and again, perhaps more than 100 times over the course of 2,500 years. Each new flood cut deeper into the landscape, deepening the riverbeds and creating new scars on the planet. It was an endless cycle of creation and destruction. The glacier dammed the river, the lake filled to critical capacity, and then the dam collapsed with a roar, unleashing another wave of chaos. Similar catastrophic floods, though not always on such a monstrous scale, occurred in other parts of North America, which was being liberated from its ice cap. The melting of another giant, the Laurentide ice sheet, created another monster, glacial Lake Agassiz. It was even larger than Lake Missoula and covered vast areas of modern-day Canada and the United States.
Although Lake Agassiz did not disappear in a single massive outburst, its drainage occurred in a series of powerful surges. Each time the ice dams gave way or new drainage channels opened, enormous volumes of fresh water rushed into the Atlantic Ocean, likely significantly affecting ocean currents and climate. On the other side of the world, in Eurasia, the melting of the Scandinavian ice sheet caused equally massive floods. In Siberia and Eastern Europe, enormous proglacial lakes formed and erupted, radically altering the region's entire river network. The collapse of ice dams carved new river valleys and deepened old ones.
Although landscapes comparable to the Missoula Barrens, they are less well studied, the underlying principle underlying these catastrophes is universal to all regions where massive glaciers interacted with complex terrain. Studying these great floods reveals the true power of meltwater and the dynamic, violent nature of the end of the Ice Age. We understand that this was not an era of slow and gradual warming. No, it was a series of violent, episodic cataclysms. These monstrous floods caused rapid and irreversible changes to the Earth's surface, shaping the landscapes we see today. They altered river courses, redistributed enormous masses of sediment, and even influenced the very topography of entire continents. Their scale testifies to the colossal energy released as the planet transitioned from the Ice Age to warmer times. But the melting ice also triggered other, equally monumental processes. As the Ice Age drew to a close, the Earth's crust itself began to shift. The disappearance of the ice cap that had been pressing upon it led to significant shifts, and during this period of dramatic change, another destructive force may have awakened: volcanoes. The idea that volcanic eruptions during melting glaciers could have influenced the climate is the subject of intense scientific debate. The key mechanism linking glacial retreat and volcanic activity is called isostatic rebound. Imagine this: during the glacial maximum, enormous continental sheets, several kilometers thick, with their monstrous mass pressed down on the Earth's crust, causing it to sag into the viscous mantle beneath. It's similar to a heavy object leaving an indentation in a soft pillow. When the ice began to melt and this gigantic mass disappeared, the Earth's crust, freed from its burden, began to slowly rebound or rise back up. This process, incidentally, continues today in regions such as Scandinavia and parts of North America at a rate of several millimeters per year. This uplift of the Earth's crust could have dramatically altered the tectonic environment. The reduced stress on the crust altered the stress in the rocks. This could have reactivated existing fault lines and, most importantly, affected magma chambers deep underground. Essentially, the disappearance of the ice cap relieved the confining pressure on the magma. This could have led to so-called decompression melting. Magma could more easily rise through weakened areas of the crust, triggering eruptions. Studies do show a link between periods of rapid glacier melt and surges in volcanic activity. For example, in Iceland, which was buried under a thick layer of ice, volcanic activity increased sharply immediately after its retreat. Similar data exists for North America and even Antarctica. But how did these eruptions affect the climate, which was already changing? Here's where things get more complicated. Large eruptions release enormous quantities of gases and ash into the atmosphere. Sulfur dioxide, when reacting with oxygen, forms sulfate aerosols, microscopic particles that act like tiny mirrors, reflecting sunlight back into space. This leads to a temporary but noticeable cooling of the planet's surface. If volcanic activity was indeed elevated during the melting period, these eruptions could have caused local or even regional cooling, slowing overall warming. Time and scale are crucial here. While a single powerful eruption may only have a short-term effect, a series of such events could have had a more significant impact. Some scientists even suggest that volcanic aerosols may have contributed to the mysterious cold period known as the Younger Dryas. If a series of large eruptions occurred at that time, their combined cooling effect could have amplified other factors, leading to a temporary return to glacial conditions. However, the primary cause of the Younger Dryas is generally believed to be dramatic changes in ocean circulation, caused precisely by the influx of massive amounts of fresh water from melting glaciers. And here the circle closes. The water currents generated by melting ice change everything in their path. Imagine a world freed from the shackles of ice, but the planet's awakening is accompanied not only by melting glaciers, but also by a fierce fire erupting from its depths. Volcanic activity, long suppressed by the colossal weight of ice sheets, breaks free. Here, in this changing world, volcanoes are becoming more than just mountains spewing lava. They are becoming the main architects of a new landscape. Each eruption reshapes the planet's map. New mountains are born from the fiery depths, and molten lava flows, like fiery rivers, burn their way through, solidifying into bizarre shapes. Clouds of ash settle to the ground, covering it in a grey shroud for miles around. But the most dramatic spectacle unfolds where fire meets ice. Imagine a volcano awakening beneath a kilometers-thick glacier. Incredible heat melts enormous volumes of ice, and a vast lake forms beneath the icy shell. The pressure grows with each passing minute, until finally the ice dam gives way. With a deafening roar, apocalyptic torrents of water, mud, and ice debris, known as Laup, burst forth. This unstoppable force sweeps away everything in its path, transforming the landscape beyond recognition. Lava and ash flows bury entire Ice Age ecosystems. Forests that survived millennia of cold are consumed in an instant. Rivers that have flowed their courses for centuries encounter insurmountable barriers and are forced to find new routes. But in the place of destruction, new life is born. Volcanic wastelands are gradually populated by pioneers, creating unique ecological niches. The migration routes of ancient herds, forged by their ancestors, are cut off, and animals are forced to find alternate routes in this chaotic, transformed world. To prove this connection between melting glaciers and volcanic eruptions, scientists are acting like true detectives. They're studying ice cores extracted from the depths of Antarctica and Greenland, where every layer of ash is a trace of an ancient eruption. They're analyzing sedimentary rocks and dating volcanic rocks, attempting to synchronize geological events. And although direct, definitive proof is still lacking, the physical model appears more than convincing. Think of it this way. Gigantic ice sheets press down on the Earth's crust with a force difficult to imagine. When this colossal weight was removed, the stress in the crust shifted. It was as if a heavy lid had suddenly been removed from a boiling cauldron. The path was clear for magma rushing to the surface. Thus, while the glaciers were changing the planet's surface, the Earth's internal forces responded with a fiery roar, adding another layer of chaos and complexity to this period of transition. But what if the biggest blow to the Ice Age came not from the depths of the Earth, but from the silent void of space? The idea that a comet or asteroid impact could have been the trigger that changed the planet's climate continues to excite scientists to this day. It is one of the most intriguing and controversial hypotheses in modern paleoclimatology. Although such cosmic impacts are extremely rare, their consequences can be immediate and absolutely devastating. Researchers around the world are searching for an answer to the question: did an uninvited guest from outer space play a fatal role in the dramatic events that unfolded at the end of the last Ice Age? Central to this theory is a mysterious period known as the Younger Dryas. Picture this. The world is slowly but surely warming. Glaciers are retreating, life is returning to the north. Then, suddenly, about 12,900 years ago, as if an invisible switch flipped, the planet was once again plunged into a freezing cold comparable to the peak of the Ice Age. This sudden climate relapse continued for over 1,000 years before global warming resumed. This sharp temperature spike, interrupting the natural process of exiting the Ice Age, is the Younger Dryas. The hypothesis posits that a comet or asteroid was the cause of this cataclysm. Perhaps the celestial body did not strike Earth directly, but exploded in the atmosphere,
breaking into numerous fragments. This explosion would have caused a global environmental catastrophe and triggered a sharp cooling. Proponents of this idea point to a multitude of clues, like investigators working at a planetary-scale crime scene. They consider the key evidence to be so-called impact markers discovered in a geological layer that precisely corresponds to the onset of the Younger Dryas. What are these markers?
First, nanodiamonds, microscopic crystals that can only form under extreme, unearthly pressure and temperature conditions. Second, magnetic spherules, tiny molten balls of rock, frozen tears of the planet. This same layer also contains anomalously high levels of charcoal and soot, evidence of massive fires. And most importantly, deposits from this period, found throughout North America, Europe, and even the Middle East, contain elevated concentrations of platinum and iridium. These elements are extremely rare in the Earth's crust, but are common components of asteroids and comets. It's a kind of cosmic signature left at the site of the catastrophe. This thin layer of sediment, which scientists call the Younger Dryas boundary layer, often appears as a black mat, rich in organic remains. Its widespread distribution suggests that the event was truly global, whether a direct impact or a series of powerful airbursts. The consequences of such an event would be truly apocalyptic. Imagine an atmospheric explosion, not tens, but thousands of times more powerful than the famous Tunguska meteorite of 1908. The shockwave would roll across entire continents, causing forest fires of unprecedented proportions. North America would be transformed into a blazing inferno. Smoke and soot from these fires would have risen into the stratosphere, releasing millions of tons of ash and dust into the atmosphere. The sky would have darkened for months, perhaps even years. Sunlight would have simply stopped reaching the surface, ushering in a so-called impact winter. Temperatures across the planet would have plummeted, disrupting all climate cycles. This rapid cooling could have been the trigger that launched the anomalous cold of the Younger Dryas, affecting atmospheric circulation and even ocean currents. One of the main casualties could have been the gigantic conveyor belt of heat in the Atlantic. The impact could have destabilized the enormous Laurentide ice sheet, which covered most of North America. As a result, a colossal volume of fresh meltwater would have poured into the North Atlantic. This flow, like an injection of icy water into the planet's circulatory system, would have stopped the circulation of the warm currents that warmed the Northern Hemisphere. Disruption of this system is one of the best-known mechanisms capable of causing abrupt and catastrophic climate change. A sudden influx of cold fresh water would have reduced the salinity and density of surface waters, preventing them from sinking to depth and disrupting the entire cycle of warm currents moving northward. This mechanism is believed by many to be the main cause of the Younger Dryas cold spell. However, like any bold theory, the cosmic impact hypothesis is fiercely criticized in the scientific community. Many researchers, while acknowledging the anomalous cooling, question its extraterrestrial origin. Critics point out that the proposed markers, nanodiamonds, spherules, and soot, are not unique. They could have formed as a result of other terrestrial processes, such as large-scale forest fires or powerful volcanic activity. Furthermore, an impact crater of the appropriate age and size that would provide irrefutable evidence has yet to be found. There are also alternative explanations. Perhaps the catastrophe occurred without any cosmic intervention. Melting ice sheets alone could have caused the outburst of the gigantic Lake Agassiz. The release of such a huge volume of fresh water into the ocean could have had the same effect, stopping the Atlantic heat conveyor. This theory is strongly supported by climate models and does not require comets or asteroids. But while the scientific debate continues, the impact hypothesis itself underscores one important point. Earth is not isolated in space. Sudden extraterrestrial events can radically alter the climate and fate of life on our planet. If such a collision had occurred, it certainly would not have ended the Ice Age. The general warming trend, caused by changes in Earth's orbit, would still have taken its toll. But this impact from space could have caused a severe temporary climate reversal, which would have had a profound impact on the flora, fauna, and early human populations of that time. The Younger Dryas is essentially an abrupt and shocking return to glacial conditions that interrupted the Great Warming at the end of the last glacial period. This period began approximately 12,900 years ago and lasted for approximately 1,200 years, after which the climate returned just as rapidly to warming, ushering in our modern era. This event offers a crucial lesson from the past. It vividly demonstrates how fragile Earth's climate system is and how quickly it can shift between states, even when the overall trend seems to be in the opposite direction. Before this cataclysm, Earth had already enjoyed several thousand years of warmth. Following the peak of the last glaciation, the planet entered a long-awaited thaw. Colossal ice sheets melted, sea levels rose, and vegetation reclaimed ever-new territories from the ice. This period, known as the Bulling-Allerud warm period, was characterized by mild and favorable conditions. But then, like a bolt from the blue, the Younger Dryas arrived. In some regions, particularly around the North Atlantic, conditions became almost as harsh as at the height of the Ice Age. Data from Greenland ice cores reveals something incredible. In just a few decades, within the lifetime of a single generation, average annual temperatures plummeted by 10 or even 15 degrees Celsius. The consequences of this rapid cooling were widespread. Glaciers, which had been retreating for centuries, halted their advance and then began to advance again. Vegetation gave way to cold-resistant species, and sea ice once again encased the North Atlantic. The most widespread theory explaining this climate nightmare points to a breakdown in the ocean current system. Imagine a gigantic, invisible river flowing right through the depths of the ocean. This isn't just a current, it's a global heat conveyor, our planet's vital circulatory system, known to scientists as the Atlantic Meridional Circulation, or AMOC for short. This colossal system acts like a giant pump. It draws warm, salty water from tropical latitudes and carries it far north into the frigid Atlantic. When this warm water reaches the polar regions, it cools, becomes heavier, denser, and sinks into the abyss, making room for a new batch of warmth from the south. It is this continuous process that warms Western Europe and parts of North America, creating a much milder climate there than would otherwise be the case at these latitudes. Now let's fast forward thousands of years to an era when the great glaciers were retreating. At the end of the Ice Age, the melting of gigantic ice sheets created entire freshwater seas. One such monster was Glacial Lake Agassiz, a colossal body of water in the heart of North America, larger than any of today's Great Lakes. And then, about 12,900 years ago, catastrophe occurred. Geological evidence indicates that the ice dam holding back the lake collapsed. Unimaginable torrents of icy freshwater gushed through the Great Lakes system and the St. Lawrence River directly into the North Atlantic. This icy deluge dealt a fatal blow to the ocean conveyor belt. Huge masses of freshwater, which is naturally lighter and less dense than saltwater, spread across the ocean's surface like a giant oil slick. They created an impassable barrier. The cooled saltwater could no longer sink to the depths, and the entire AMOC mechanism slowed and then perhaps stopped altogether. The planet's great heat pump was shut off. The consequences were immediate and horrific. Without a warm current, the North Atlantic and the surrounding continents rapidly returned to a glacial nightmare. Sea ice began to advance, its white surface reflecting sunlight back into space, further cooling the planet. This regional collapse triggered a chain reaction across the globe. Atmospheric currents shifted direction, tropical regions were engulfed in severe drought, and the monsoon system was completely thrown out of balance. Evidence of this ancient catastrophe remains on the ocean floor today. In sediment cores, paleontologists are seeing a dramatic shift in microorganisms. Warm water species disappear, giving way to cold water species. The very composition of bottom sediments also changes, indicating a complete halt in deep-sea currents. While the freshwater lake outburst theory is the leading one, there's another, more explosive hypothesis. Some researchers suggest that the sharp cooling event known as the Younger Dryas was caused by a cosmic event. Imagine a comet or asteroid plunging into Earth's atmosphere and exploding over the ice sheet. Proponents of this idea point to evidence such as layers of soot from massive forest fires, which they believe engulfed an entire continent, and other markers of extraterrestrial impact. However, the scientific community is largely skeptical of this theory. Many believe the existing evidence is inconclusive, and the freshwater outburst mechanism provides a far more logical and complete explanation for all the observed climate anomalies. The Younger Dryas event was a crucial lesson for us. It brutally demonstrated how fragile Earth's climate balance is and how deeply it depends on seemingly immutable factors like ocean currents. We learned that the transition out of the Ice Age was not a smooth and gradual process of warming. It was a journey full of sharp turns and catastrophic reversals. This knowledge about the ancient past is crucial for understanding our future. It shows that even under conditions of global warming, sudden and severe cooling is possible in certain regions if one of the planet's key systems reaches its tipping point. The melting of ancient ice changed ocean currents and plunged the world into chaos, a stark reminder of the complex and unpredictable force that is our planet's climate. Approximately 12,000 years ago, as the last ice age finally ended, another monumental drama unfolded on the planet. It was the time of the Great Extinction. An entire world of gigantic animals, known as megafauna, disappeared from the face of the Earth. This process affected every continent, but nowhere was it as devastating as in North and South America, as well as across the vast expanses of Eurasia. Understanding what exactly killed these titans is one of the greatest mysteries of paleontology, one that scientists are still grappling with. Megafauna are giant animals weighing over 45 kilograms, and the Pleistocene world was their realm. Just imagine North America at that time. Herds of mighty woolly mammoths, Mammothus primigenius, and mastodons roamed its vast expanses. They were hunted by deadly saber-toothed cats, Smilodon, dire wolves, Enochian dirus, and giant short-faced bears, Arctidus simus, predators that would dwarf today's grizzlies. Giant ground sloths the size of elephants and even American camels also inhabited this land. Today, not a trace of this magnificence remains. They are all extinct. South America lost no fewer unique creatures. It was home to giant glyptodont armadillos, resembling living tanks, various species of ground sloths, and toxodons, strange creatures resembling hippopotamuses with rhinoceros horns. In Eurasia, woolly rhinoceroses, enormous cave bears, and mighty cave lions disappeared from the scene. However, some species, such as reindeer and bison, managed to survive. Interestingly, Africa and South Asia were largely unaffected by this extinction. Many of their giants, including elephants and rhinoceroses, survive to this day. The timing of these events is crucial. In both Americas, the extinction occurred incredibly quickly, practically instantaneously in geological time. The peak of this catastrophe coincided with the end of the Younger Dryas cooling period, approximately 10,000 to 12,000 years ago. And most importantly, it was precisely at this time that the first humans arrived on the continents. In Eurasia, the process was more drawn out. Some species disappeared earlier, others later. But the sheer speed and scale of the extinctions leave no doubt. Some colossal blow struck the ancient world, whether by the force of nature or the activity of a new intelligent predator. So, what killed the giants? Scientists put forward two main theories, which were long bitter rivals but are now increasingly seen as parts of a single picture. The prime suspect is a dramatic climate change. As the glaciers retreated, the world began to change rapidly. The endless cold steppes, the so-called mammoth prairies, which had supported countless herds of herbivores, disappeared before our very eyes. Dense forests, swamps, and thickets of scrub grew in their place. For animals perfectly adapted to the cold, open landscape, this was a death sentence. Their food supply disappeared. Furthermore, the climate became more extreme, with hot summers and cold winters. not all animals were able to adapt to such changes. Melting ice caused massive floods, and sea levels rose, inundating coastal plains and cutting off animal populations from each other. It's quite possible that new diseases emerged in this chaos, decimating the weakened giants. The second and prime suspect is humans. This hypothesis, known as the extinction theory or blitzkrieg theory, places the primary blame on our ancestors. Imagine, when the first humans arrived in America, they found themselves in a veritable lost world, inhabited by giants who had never seen a human before. These animals were naive and lacked the instinctive fear of a two-legged predator. Yet humans were already incredibly effective hunters. Armed with spears tipped with sharp stone, they could strike targets from a distance. People hunted in groups, using complex strategies and trapping even the largest and most dangerous animals. The speed with which humans colonized both American continents strikingly coincides with the extinction wave. According to this theory, a wave of hunters swept across the continents, wiping out population after population. Megafauna, with their slow reproductive cycles, simply couldn't replenish their numbers. Africa provides indirect confirmation of this theory. Where humans and giant animals evolved side by side for hundreds of thousands of years, extinction was minimal. Over a long and bloody history of coexistence, African elephants and rhinoceroses learned to fear humans and developed effective defense strategies. American mammoths simply didn't have such a chance. There is a third point of view, which is becoming increasingly popular today. Most modern scientists lean toward an idea that combines several factors into a single devastating force. Imagine not one killer, but two, acting in deadly collusion. This combined effects hypothesis tells us that neither global climate cataclysms nor the emergence of a new predator, humans, could have wiped out entire giant species on their own. But together, their impact proved fatal. We are transported to a world already bursting at the seams. Relentless and drastic climate change was sapping the strength of megafauna, leaving them weak and defenseless. Their vast habitats, stretching for thousands of kilometers, began to disintegrate into isolated pockets of survival. Their usual food sources were disappearing, and constant stress likely made these giants easy prey for new, unprecedented diseases. And at this very moment, when populations were already teetering on the brink, a new, incredibly intelligent and effective hunter entered the picture. Even the slightest pressure from this hunter was the final straw, the fatal blow that brought down the entire ecosystem. The picture that emerges is tragic. Global warming, for example, is compressing the habitat of enormous animals, driving them into tiny pockets of land. Here, trapped, they become ideal targets for hunters. The disappearance of these titans was a turning point in the history of the planet, forever changing its appearance. The loss of giant herbivores and colossal predators reshaped the vegetation, disrupted ancient nutrient cycles, and shattered the millennia-old drama of the relationship between hunter and prey. Studying the causes of this ancient catastrophe is more than just a look into the past. It offers a crucial lesson for us living today, trying to preserve the remnants of nature's former splendor. It perfectly demonstrates how fragile and interconnected the world is, where climate, ecosystems, and the activities of a single species can determine the fate of all life on Earth. Climate undoubtedly played a major role in this widespread tragedy that unfolded at the end of the Ice Age. And while many theories place the blame on humans, it is undeniable that rapid and brutal climate swings laid the foundation upon which the extinction drama played out. They were either the primary driving force or the critical factor that brought these giant animals to their knees, leaving them vulnerable to everything else. The speed and scale of these changes presented a challenge that many megafauna species simply couldn't cope with. They were perfectly adapted to the harsh but stable conditions of the glacial world and were unprepared for the new reality. One of the most dire consequences of climate change was the loss of their home. Vast areas of the northern hemisphere during the glacial maximum were covered in a unique ecosystem that scientists call the Mammoth Steppe. It was a true paradise for giants, a boundless cold ocean of highly nutritious grasses, grains, and sedges. Colossal herds of woolly mammoths, mighty woolly rhinoceroses, and steppe bison thrived here. But then the world began to melt. As the ice sheets retreated and the planet warmed, this rich steppe biome literally vanished before our eyes. Entirely new landscapes arose in its place. Dense, dark forests advanced from the north, displacing open spaces. Melting glaciers created gigantic wetlands, while in other regions, droughts set in, and deserts devoured fertile lands. Animals, whose entire evolution had been honed for life in open, cold grasslands, found themselves trapped. Their world shrank, fragmented into small, isolated pockets. This not only hindered food searches and seasonal migrations, but also led to degeneration, since inbreeding was inevitable in isolated populations. The sheer speed of climate change was a colossal stress. The warming at the end of the Ice Age was not a smooth, gradual process spread over thousands of years. No, it was a veritable planetary fever. It was accompanied by sharp temperature spikes, such as the Beringia warming, and sudden returns to icy cold, as during the Younger Dryas. These rapid changes, sometimes occurring in just a few generations, presented an insurmountable challenge for large animals with their slow reproductive cycles. Species perfectly adapted to stable cold suddenly found themselves in a world that was changing faster than they could adapt. Imagine this swing, from cold and dry to warm and humid, and then back again to an icy hell. This ecological instability undermined the very foundations of their existence. As the climate changed, so did their diet. With the disappearance of the mammoth steppe, the nutritious grasses on which the giants depended were replaced by other, less calorific or even poisonous plants. Forests, for example, cannot feed a multi-ton herd the way open pastures did. These dietary changes caused nutritional stress, weakening the animals, making them easy prey for predators or disease. Even for forest dwellers like mastodons, the changing composition of forests could mean starvation. The giants' immune systems, weakened by the loss of their home and constant malnutrition, couldn't cope. Their bodies became defenseless. Sudden changes in temperature and humidity could trigger the spread of new deadly pathogens and parasites, to which the megafauna had no immunity. And since the animals were forced to huddle in tightly packed groups on the last remaining islands of habitable territory, the risk of infection increased exponentially. These refugees turned into death traps. High water levels also played a role. As the glaciers melted, sea levels rose rapidly, inundating vast coastal plains. These had once been rich pastures and vital migration corridors. To make matters worse, gigantic glacial lake outburst floods caused catastrophic floods like the Missoula floods. Imagine skyscraper-tall walls of water roaring through valleys, wiping out landscapes, destroying vegetation, and killing millions of animals in their path, or forever cutting off populations from one another. Thus, while one hypothesis blames human hunters, another, the climate hypothesis, emphasizes that megafauna populations were already under monstrous environmental pressure. They were weakened, cornered, and on the brink of extinction even before humans arrived on their lands. The climate created ideal conditions for disaster, setting the stage for extinction. In such a situation, even moderate pressure from hunters could have been fatal. On the other hand, human activities could have exacerbated this climatic stress. For example, the use of fire to clear land or hunting along migration routes further destroyed fragile habitats. Overall, the end of the Ice Age was an era of unprecedented environmental upheaval. The collision of two forces, massive climate change and the emergence of a new intelligent predator, created a true cataclysm that led to the rapid and widespread extinction of the world of giants. Now let's look at this story from a different perspective. There's a theory that human hunting played a major, and in some cases decisive, role in the extinction of megafauna. This concept is known as the overkill hypothesis. It posits that as human populations grew and spread across the planet, their hunting zeal and efficiency became an unbearable burden for large animals. ultimately leading to their complete extinction. This hypothesis is particularly compelling for continents where humans arrived relatively recently, such as North and South America. It is based on several key observations. First, there is a strikingly clear temporal correlation. As soon as traces of ancient humans appear on a continent, a rapid extinction of megafauna begins almost immediately. In North America, most giant mammals disappeared in a remarkably short period of time, just a few centuries. And this time coincides perfectly with the rise of the Clovis culture, famous for its deadly spears, around 13,000 years ago. This lightning-fast extinction, often referred to as a prehistoric blitzkrieg, clearly indicates that a new, incredibly powerful and destructive force invaded the ecosystem. Secondly, the hypothesis points to the fatal naivety of animals unfamiliar with humans. In Africa and much of Eurasia, large animals evolved alongside our ancestors for hundreds of thousands, if not millions, of years. They had time to develop defense mechanisms. They learned to fear and avoid humans, and their populations adapted to a certain level of hunting pressure. But when humans first arrived in the Americas, they found themselves in a kind of lost world. They encountered giants who had never seen such a predator before. Mighty mammoths, mastodons, giant ground sloths, and wild American horses possessed no innate fear of this new, bipedal, highly intelligent, and technologically advanced creature. Hunting these unafraid populations was laughably easy. This made them especially vulnerable to this new super predator. Thirdly, the effectiveness of ancient hunters cannot be underestimated. Let's travel back in time to the harsh world of the Stone Age and look at the arsenal of our distant ancestors. Early human technologies may seem primitive to us, but we shouldn't be fooled by their simplicity. In the hands of an experienced and well-coordinated group of hunters, these tools turned into deadly weapons. Imagine a hunting scene. The development of projectile weapons, such as spears, which could be thrown with tremendous force using special devices called spear throwers, was a true revolution. Now, ancient humans didn't have to get up close and personal with an enraged giant. They could deliver lethal blows from a safe distance, greatly increasing their chances of survival and success. But that wasn't all. Humans learned to use nature itself as a weapon. Fire, for example, became a tool for driven hunts, sowing panic in herds and directing them in the right direction. Ingenious traps hidden in the forest thicket, and of course team tactics, with dozens of people acting as a single organism. All this made hunting incredibly effective. One of the most spectacular methods was driving entire herds of animals toward cliffs or into natural canyon traps, where they stood no chance. Archaeology provides us with irrefutable evidence of these prehistoric dramas. All over the world, scientists are discovering ancient human sites where stone knives and scrapers lie mixed with the bones of mammoths, mastodons, and giant bison. Just imagine the caloric value of such a kill. The carcass of a single enormous animal could feed an entire tribe for weeks, even months. It's no wonder megafauna were the most coveted target for any hunter-gatherer clan. However, these giants had their Achilles heel, their reproductive rate. Large animals typically operate on a different biological clock. They have a long gestation period, giving birth to only one, rarely two, young, and it takes many years for these young to grow up and produce their own offspring. This meant their populations grew painfully slowly, and herein lies the tragedy. If hunters killed animals faster than they could be born and mature, even seemingly insignificant pressure could trigger an irreversible process. The population would begin to decline rapidly, and at some point it would reach a point of no return, from which the species could never recover. This slow rate of reproduction could have been one of the main reasons why megafauna were unable to adapt to the new, changed world. Their biology made them incredibly vulnerable to the onslaught of a new super predator: humans. Unlike smaller, rapidly reproducing animals, the giants simply couldn't replenish their losses. This hypothesis of total extermination is confirmed by the fossil record, like an ancient crime report. For example, we see that extinction primarily affected large-bodied animals, while smaller species suffered much less. Another ominous fact: the most devastating waves of extinction swept across continents that humans settled relatively late: North and South America, Australia. In Africa, where humans and megafauna evolved side by side for millions of years, no such catastrophe occurred. Take Australia. Humans arrived there about 65,000 years ago, and almost immediately afterward, its unique megafauna, giant kangaroos, tiger-sized marsupial lions, and other incredible creatures, disappeared from the face of the Earth. This is a very compelling argument in favor of the human factor. However, it would be too simple to place all the blame solely on our ancestors. Today, most scientists tend to believe that there was not a single cause, but a perfect storm, a deadly duet of two factors: abrupt climate change and ruthless hunting. On the one hand, the planet itself was rebelling against its giant children. The climate was rapidly changing, familiar landscapes were disappearing, forests were giving way to steppes, and drought was setting in. All this undermined the food supply, weakening megafauna populations, making them more vulnerable to hunters. Imagine herds trapped in small patches of land, oases in the middle of otherwise uninhabitable terrain due to climate change. There, they became incredibly easy prey. Food shortages left them weak and sick. This balance of factors likely varied for each species and each region. Some giants may have been particularly sensitive to drought, while others, more resilient, fell victim to their human counterparts. While debate continues in the scientific community, one thing is clear: ancient hunters played a colossal role in shaping the world that emerged from the ruins of the Ice Age. This is one of the first and most dramatic examples of how human activity has had a profound and irreversible impact on biodiversity across the planet. And so, the Great Glacier began to retreat. Imagine these colossal ice sheets, kilometers thick, covering vast swaths of continents. About 19,000 years ago, they began to melt. By 10,000 years ago, this process was largely complete, and the face of the Earth was transformed beyond recognition. Where once there had been an icy desert, entirely new landscapes now sprawled. This great melting process gave birth to new forests, vast meadows, and vast wetlands, creating the natural diversity we see in the world today. One of the most dramatic transformations was the advance of forests. At the peak of glaciation, vast tracts of the northern hemisphere, especially in Europe and North America, were treeless tundra and frigid steppes. If forests existed at all, they were confined to small, isolated refuges somewhere in southern Europe or in sheltered valleys. But as the climate warmed and moisture increased, pioneer trees such as birch and pine began their great march north, conquering the ice-free lands. Over millennia, these pioneers gave way to the more complex and diverse forests of the temperate zone. Mighty oaks, elms, and maples appeared, as well as the giant conifers, spruce and fir. This forest advance completely changed the face of the continents, transforming open, windswept expanses into dense, dark thickets. The growth of these new forests also had significant ecological consequences. It created new habitats for animals and even affected the composition of the atmosphere. Along with the forests, new grasslands emerged, completely unlike the cold steppes of the Ice Age. As the climate warmed, areas previously bound by permafrost transformed into lush, temperate grasslands. These grasslands, far richer and more diverse than their predecessors, became home to new species of herbivores. In North America, for example, the Great Plains became a boundless ocean of grass, capable of supporting millions of bison herds. The character of these new grasslands, of course, varied depending on the soil and climate, but they all marked a complete departure from the cold and dry conditions of the Ice Age. The end of the Ice Age witnessed another striking transformation of the landscape, an explosive growth in the number of wetlands, lakes, rivers, and marshes. As the giant ice sheets melted, they released truly colossal volumes of water. This meltwater filled the depressions and basins left by the glacier, forming countless new lakes. These lakes varied in size, from small round lakes formed where melted ice blocks had been to gigantic periglacial seas. Such a lake, for example, was Lake Agassiz in North America, which exceeded the surface area of all the modern Great Lakes combined. Many of these bodies of water were temporary and eventually dried up or shrank, but thousands upon thousands of them remain to this day. Look at a map of Scandinavia, Canada, or the northern US. All are the legacy of the Great Melt. This same process also created vast bogs, swamps, and marshes in low-lying areas with poor drainage. Meltwater saturated the soil, creating ideal conditions for moisture-loving vegetation. These wetlands became vital ecosystems, home to a huge diversity of plants and animals, and began to play a key role in the global carbon cycle. Permafrost, which had been thawing for millennia, also contributed. An impermeable layer of ice beneath the ground surface trapped water, creating ideal conditions for the growth of bogs. But it wasn't just the surface that was changing. The very ground itself was changing. After the enormous weight of the ice sheets lifted, the Earth's crust, as if breathing a sigh of relief, began to slowly rise. This process, known as isostatic uplift, continues in some regions to this day. This uplift altered the topography, affected river courses, and created new coastlines. Vast quantities of sediment, clay, sand, gravel, and boulders carried by the glacier were deposited on the new lands, forming new soil types. It was from these glacial deposits that, over time, many of the world's most fertile agricultural lands were formed. As a result, a completely new mosaic of landscapes emerged. A world of ice and frigid steppe gave way to a world of forests, temperate grasslands, and countless freshwater bodies. This created new ecological niches and opened up new opportunities for those who managed to survive. This global environmental restructuring had a direct impact on the distribution and evolution of plants and animals, which, in turn, had profound consequences for humanity. As the world changed, so too did human survival strategies. The age of giant hunters was drawing to an end. A new era was beginning, an era of exploiting the diverse resources offered by this new, reborn world. Imagine a world just freed from its icy captivity. New landscapes, carved and polished by gigantic glaciers, became the very stage on which the entire future history of humanity would unfold and modern ecosystems would emerge. When the titanic glaciers that had shrouded the planet began to retreat, they unleashed a force capable of reshaping entire continents. The melting of these ice sheets triggered truly fundamental, global changes in river systems around the world, especially in areas where kilometer-high walls of ice once towered. Colossal volumes of meltwater, mixed with billions of tons of rock, sand, and clay, gushed across the plains. This power didn't just flow, it created. It carved new riverbeds that would shape the development of future civilizations. During this era of great change, the valleys were transformed beyond recognition, forming the very waterways that feed our planet to this day. This was the era of the Great Flood, a time when water was the Earth's primary sculptor. Let's travel even further back in time, before the Great Ice Age. Back then, rivers flowed along long-established routes, carved out according to ancient topography. But the advance of glaciers, those slow but inexorable ice monsters, disrupted this order. Glaciers acted like giant bulldozers and impassable dams. They blocked existing river valleys, forced flows to reverse course, and sometimes even buried entire drainage systems. Let's look at North America. The advance of the colossal Laurentide ice sheet, named for the Laurentide Plateau, forced ancient rivers to seek new routes to the ocean, literally pushing them north, forcing them to flow along the very edge of the ice. This led to the formation of gigantic proglacial lakes, which, overflowing, broke through their icy banks, and then true chaos ensued. The water carved entirely new channels in the earth. And now the climate is changing again. The ice sheets are beginning to melt. Imagine this process, not just trickling streams, but the release of unimaginable quantities of water.
These torrents, roaring from the ice fronts, gave birth to monstrous rivers, sinuous and mighty. They weren't just numerous, they were incredibly powerful, far exceeding in volume and destructive force the modern rivers flowing in the same areas. They dragged along not just sand and gravel, but entire mountains of debris, boulders the size of houses, billions of tons of rock stripped from the face of the earth and ground down by the glacier. All of this settled on the plains, creating new geological layers. The speed and force of these meltwater flows were such that they wielded monstrous erosive power. This water didn't just flow, it sliced through bedrock like a knife through butter, deepening old valleys into grand canyons or carving out entirely new ones. The impressive gorges and valleys we see today in many northern regions are the scars left on the planet by this roaring meltwater. One of the most dramatic phenomena of that time was the so-called capture of river systems. As ice sheets retreated, they exposed new lowlands and new, shorter drainage routes. Rivers, previously icebound and forced to flow along long, circuitous paths, suddenly found new, direct routes to the sea, abandoning their old channels forever. This process, known to geologists as stream capture, radically altered the size and boundaries of river basins. Take a look at the modern Ohio River in North America. Its current course is a direct legacy of the Ice Age. It became the main channel through which the gigantic Laurentide ice sheet discharged its meltwater into the ocean. Similarly, glaciers reshaped the course of the mighty Missouri River. And the Great Lakes system in North America is a monument to the Ice Age, a striking example of how melting ice can create entire inland seas. The basins of the Great Lakes themselves were literally gouged out by the erosive force of the Laurentide ice sheet. When the ice retreated, these gigantic depressions filled with meltwater, giving rise to a chain of proglacial lakes, which eventually became the Great Lakes we know today. Their shapes and connections changed repeatedly as the land, freed from the weight of the ice, slowly rose, creating temporary waterways and triggering large-scale processes of water redistribution. Let's move on to Europe. Here, the melting of the Scandinavian ice shelf caused equally dramatic changes. The Baltic Sea, for example, experienced several stages in its development. Initially, it was home to a gigantic freshwater lake, the Baltic Ice Lake. Periodically, it would catastrophically burst, discharging its waters into the ocean, then become isolated again, until finally a permanent connection with the Atlantic was established, turning it into a brackish sea. All the rivers flowing into this region experienced the colossal impact of these processes, changing their courses and water levels. The consequences of these Ice Age river revolutions are still visible in the landscape today. Many modern rivers flow through valleys created or radically modified by glaciers and their meltwater. High terraces along the riverbanks, formed from glacial deposits, are silent witnesses to times when water levels were much higher and streams rushed with furious speed. Sand and gravel deposits found along the riverbeds also testify to the incredible water activity during the Great Melt. But these changes were more than just a geological drama. They had colossal consequences for the entire ecosystem and, of course, for the first humans. The emergence of new, full-flowing rivers opened up access to fresh water, created incredible fishing opportunities, and paved new migration routes for animals and humans. But there was a flip side. These same rivers carried the threat of monstrous floods and unpredictable riverbed shifts, requiring ancient tribes to constantly adapt and survive. The transformation of river systems at the end of the Ice Age was a dramatic and striking demonstration of how quickly the Earth can change under the influence of global climate shifts. The melting of massive ice sheets led to another monumental consequence, the birth of a vast number of new freshwater bodies, primarily vast lakes. These lakes varied greatly in size, water composition, and longevity, but they all shared a common source: colossal volumes of meltwater released from disintegrating glaciers. Their emergence not only transformed landscapes, but also created new ecological niches, which life immediately began to inhabit. One of the most impressive types of such bodies of water were proglacial lakes. These were true inland seas, forming at the very edges of retreating ice sheets. Their shores were often formed by the ice itself or by moraine ridges, walls of rock and clay left behind by the glacier. The greatest example of such a body of water is glacial Lake Agassiz in North America. This gigantic lake spread across the very center of the continent as the Laurentide ice sheet began to retreat northward. At its peak, Lake Agassiz was larger in area than all of the modern Great Lakes combined, covering parts of today's Canadian provinces and American states. It contained nearly 20,000 cubic kilometers of water. Today, the lake is gone, having dried up, but in the past, it periodically erupted through various vents, and these outbursts were catastrophic. Huge flows of fresh water rushed into the ocean, having a significant impact on global circulation and the planet's climate. Another famous proglacial lake was Lake Missoula, formed by the tongue of the Cordilleran ice sheet in western Montana. This lake's fate was even more dramatic. An ice dam repeatedly blocked a valley, the lake filled to a critical level, and then the dam burst. This led to a series of monstrous floods that literally washed away everything in their path. The landscape known as the channeled scablands in eastern Washington was carved by these floods, which repeated over millennia. They left behind a unique landscape of dried-up waterfalls hundreds of meters high and deep canyons. The formation and drainage of such gigantic lakes played a key role in the redistribution of water and sediment across the continent. Beyond these colossal examples, thousands of other, smaller, periglacial lakes formed in regions that experienced glaciation. In Europe, as we've already mentioned, the Baltic ice lake filled the basin of today's Baltic Sea when the Scandinavian ice sheet retreated. It underwent a complex evolution, sometimes connecting with the ocean, sometimes becoming fresh water again, until it became the salty Baltic Sea we know today. These periglacial lakes were crucial elements of the new landscape. They served as gigantic temporary reservoirs for meltwater and even influenced the regional climate, significantly reducing air temperatures. Another, more common type of glacial lake existed, the so-called kettle lakes. These are relatively small, often perfectly circular bodies of water. They formed when huge chunks of dead ice, carved from a retreating glacier, became buried under a layer of sand and gravel. As these underground ice flows slowly melted over decades or even centuries, they left behind deep depressions that later filled with water. Such kettle lakes abound in regions once covered by ice, such as Wisconsin and Minnesota in the United States, as well as in many parts of Canada and northern Europe. Their abundance is a clear testament to the chaotic and uneven melting of the great glaciers. Finger lakes are another distinctive type of glacial lake, particularly prominent in upstate New York. These long, narrow, and incredibly deep lakes, resembling the fingers of a giant hand, typically formed in pre-existing river valleys. An advancing glacier, moving down such a valley, acted like a giant plow, deepening and straightening it. When the ice retreated, these excessively deep valleys filled with meltwater, creating the characteristic elongated lakes. Finally, cirque lakes, also known as tarns or cirque lakes, are small, often circular lakes that form in mountain bowl-shaped depressions carved by glaciers near peaks. Let's move on to a world bound by ice. The climate of the Ice Age was a paradoxical phenomenon. Despite gigantic ice sheets covering the continents, the planet as a whole suffered from horrific drought. Imagine, colossal volumes of water were literally frozen, removed from the global circulation. As a result, there was far less moisture left in the atmosphere, ready to fall to the ground as rain. This led to deserts and arid steppes beginning their relentless advance on those corners of the world we know today as flourishing and fertile. Vast expanses of North America and Eurasia, now covered with fields and forests, were parched, dusty plains in that distant era. This aridity either supported only the most resilient vegetation or turned the land into a lifeless wasteland. Enormous and stable high-pressure systems formed above the ice caps. These cold air masses, like invisible walls, pushed the storm fronts we know closer to the equator.
As a result, regions that today are drenched in tropical downpours could have been as dry as gunpowder during the Ice Age. But nature abhors a vacuum. At the same time, some modern deserts received more moisture. For example, in the southwestern United States, these climate shifts brought so much precipitation that they formed enormous freshwater lakes, which no longer exist today. Another hallmark of that era were the winds. Not just any winds, but incessant hurricane-force currents of icy air. They were generated by the colossal temperature difference between the frozen, ice-covered continents and the relatively warm waters of the oceans. This contrast created a powerful pressure gradient, generating winds that roared across the devastated landscapes. These invisible rivers of air played a key role in shaping the world. They picked up billions of tons of fine dust, known to geologists as loess, from glacial wastelands and carried it thousands of kilometers. These deposits, as they settled, created incredibly fertile soils. In some regions, such as China and the central United States, this loess layer is now tens of meters thick, and it is here that the richest agricultural lands on the planet are located. But the winds also had a dark side. They brought with them a piercing cold, turning even ice-free areas into icy hells. Fierce blizzards and deadly frosts were the norm. This combination of low temperatures and hurricane-force winds created a unique environment where permafrost reigned. The soil here froze many meters deep and did not thaw for years, even decades. The permafrost gave rise to bizarre landscapes, such as patterned earth, where rocks, driven by cycles of freezing and thawing, were arranged into almost perfect geometric shapes. The Ice Age world was a realm of astonishing ice sculptures sculpted by nature itself. From giant ice wedges to pingos, enormous hills with ice cores inside. The climate was merciless: long, dark, bone-chilling winters and short, cool summers. Any living creature that dared to exist in the shadow of the ice sheets faced a daily, desperate struggle for survival. Cold, dryness, and merciless winds, the three horsemen of the apocalypse, ruled this harsh and inhospitable world. Hunters. The Ice Age ecosystem was more than just a food chain, but a vast and brutal arena. Here, giant herbivores were a living resource, and powerful predators were ruthless hunters, waging an eternal war for survival. This complex game, the rules of which were dictated by the harsh climate, gave rise to unique attack strategies and sophisticated defenses. To hunt prey the size of a house, predators themselves had to become true monsters. Among the most dangerous killers of that era were not only the obvious candidates. Giant ground sloths, despite their colossal size, could be surprisingly fast and agile, using their massive size to launch deadly attacks. Jaguars, the embodiment of grace and speed, were masters of surprise ambush attacks. Each predator honed its unique skills to secure its place at the top of the food chain. But the true king of terror was the saber-toothed cat, Smilodon fatalis. Its kingdom stretched across North America, and its relatives inhabited other continents as well. These magnificent creatures were renowned for their incredible fangs, 2 deadly blades that could grow up to 18 centimeters long. Despite their name, saber-toothed cats were not direct ancestors of modern cats, but belonged to an entirely separate, extinct lineage of predators. Their build was not feline, but rather bear-like, incredibly powerful, stocky, and muscular. This suggests they weren't runners, but masters of ambush, a shadow lurking in the tall grass. Their monstrously powerful forepaws were designed for one purpose: to grab and hold huge, struggling prey. Then came the fangs. They weren't designed for fighting or crushing bones. In fact, these blades were quite fragile. Their purpose was to deliver a single, precise, and fatal blow to the neck, severing the trachea and major arteries. The prey died from rapid blood loss, unable to inflict any retaliatory injury. It was the surgical precision of a killer. Smilodon hunted the largest and most clumsy inhabitants of the Ice Age: mammoths, mastodons, giant sloths, and ancient bison. Fossil finds, especially from the famous La Brea tar lakes, reveal entire groups of Smilodon that died together. This suggests that they may have lived in prides like modern lions. Hunting together gave them a huge advantage against prey that weighed several times their own weight. Another apex predator that terrorized the ancient plains was the dire wolf, Canis dirus. These wolves were significantly larger and more massive than their modern grey counterparts, reaching weights of up to 70 kilograms. Their jaws were designed for crushing bone, making them not only effective hunters, but also excellent scavengers, capable of crunching through the skeleton of any prey. Dire wolves were social predators that hunted in massive packs. This strategy allowed them to outsmart even the largest animals. Their diet included bison, wild horses, camels, and even baby mammoths. Their tactics were radically different from the ambush hunting of the Smilodon. Dire wolves turned the hunt into a marathon of death, driving their prey through relentless pursuit and coordinated attacks until they collapsed from exhaustion. Their social structure was likely highly complex, with a clear hierarchy and a well-developed system of communication within the pack. Another giant ruled the vast expanses of Eurasia and North America: the cave lion, Panthera spelaea. It was one of the largest cats in history, surpassing even the modern African lion in size. The name cave lion is misleading. Lions did not live in caves permanently, but used them as temporary shelters and safe dens for breeding. These predators combined incredible strength and agility. Their prey included reindeer, horses, bison, and young mammoths. Their social behavior is still debated. Perhaps they lived in small groups or were more solitary hunters than their African relatives. In cold climates, their strategy was based on stealth, followed by a powerful, explosive charge, relying entirely on the crushing force of the first strike. And alongside them lived a colossal hermit, the cave bear, Ursus spelaeus. These giants reached the size of modern polar bears. Analysis of their teeth shows that their diet consisted largely of plant matter, grasses, berries, and roots. However, they were omnivores and, like all bears, were not above scavenging or taking prey from other predators. They were not active hunters of large game, but these mighty creatures were true warriors, capable of defending their territory from any intruder. Their main role in the ecosystem was to process vast amounts of vegetation and maintain the forest. They received their name from their habit of spending the long winter months in deep caves. The list of super predators doesn't end there. North America was home to the short-faced bear Arctodus, an incredibly fast and powerful predator that was arguably the most fearsome carnivore on the continent, capable of both actively hunting and snatching prey from any creature. Spotted hyenas and ancient crocodiles also expanded their reach across Eurasia, performing the vital work of hunters and scavengers, clearing the landscape of the remains abandoned by other killers. These courageous hunters faced incredible challenges. In the perpetual cold, any hunt required colossal energy expenditure. Prey could be rare or scattered across vast territories, and the giant herbivores themselves were deadly, capable of killing or maiming an attacker with a single blow of their foot or horn. This sparked a veritable evolutionary arms race. Prey grew thick hides, increased in size, developed powerful limbs for defense, and flocked into herds. In response, predators honed their deadly weapons, like the fangs of the Smilodon, or developed complex cooperative hunting strategies like packs of dire wolves. But a new, more unpredictable and intelligent predator entered this arena: humans, a representative of the species Homo sapiens. In the late stages of the Ice Age, our ancestors became the dominant force. Ancient hunters developed sophisticated tactics and deadly weapons: spears with stone tips, spear throwers that allowed them to strike targets from a distance, and ingenious traps. They turned hunting into an art. Fast forward to an era when the great glaciers retreated, revealing a ravaged land. Look at these mountain landscapes. Here, in giant bowls carved by ice like ancient amphitheatres, new worlds are born. As the ice giants melted under the onslaught of heat, their meltwater rushed down, filling these basins and creating countless new lakes. At the very end of the Ice Age, this event became a true revolution for the entire ecosystem. These newborn lakes became lifelines. They carried not just fresh water, but entire ecosystems destined to be populated. Life began to teem in their transparent depths. Countless species of fish, amphibians, and tiny invertebrates emerged, creating a complex food chain from scratch. Moreover, these bodies of water became vital oases, resting and feeding points for migratory birds on their long journeys. For the ancient people who inhabited these lands, the appearance of the lakes was a true gift. They gained access to an inexhaustible food source in the form of fish and to the purest drinking water, which radically changed their way of life, influencing their choice of campsites and their very survival strategies. But the most astonishing thing is that these lakes have become a kind of time capsule. The sediments that accumulated at their bottoms over centuries now constitute a priceless archive. They contain pollen from ancient plants, the remains of microscopic organisms, and other traces that allow scientists, like detectives, to reconstruct the climate and environment of the distant past. They are a window into the evolution of our planet. However, the very process of these lakes' birth was intimately intertwined with the colossal geological forces that continued to reshape the Earth. Imagine a giant mattress from which an unimaginable weight had just been removed. The Earth's crust, freed from billions of tons of ice, began to slowly, inexorably rise. This process, known as isotropic recoil, was capable of the incredible. It could tilt an entire lake, causing its waters to flow into a new valley, or drain it completely. In other cases, the uneven uplift of the Earth's crust created entirely new depressions, which immediately filled with meltwater. So, the birth and life of these lakes was a dynamic, ever-changing process, influenced by both the rapid melting of ice and slow but powerful geological forces. And today, looking at the countless lakes dotting the northern hemisphere, we see the living legacy of the Ice Age. They are silent witnesses to the dramatic transformations that our planet experienced during the Great Ice Age. With the retreat of the glaciers, a new era dawned for humanity, requiring a radical restructuring of its entire way of life. People accustomed to surviving in the harsh cold found themselves confronted with a world that was changing literally before their eyes. Glaciers retreated, landscapes were transformed, and humans were forced to adapt to these dramatic changes. Survival now depended on more than just the ability to track and bring down gigantic beasts. The time had come to seek new, far more diverse sources of food. This turning point in history, known in Europe as the Mesolithic and in the Americas as the Archaic period, was a time of great inventions. Humans created new tools, mastered new technologies, and forged new social networks to find their place in this rapidly changing world. One of the key challenges was the abandonment of hunting megafauna, the gigantic animals of the Ice Age. At the height of the cold, human communities, such as the famous Clovis people in North America or the Paleolithic hunters of Eurasia, relied entirely on herds of mammoths, mastodons, woolly rhinoceroses, and enormous bison. These giants were walking supermarkets. They provided tons of meat and fat, durable hides for clothing and shelter, and bones used to craft the most durable tools. But with the end of the Ice Age and climate change, their world collapsed. Many of these colossal creatures became extinct, vanishing from the face of the Earth forever. This forced humans to completely rethink their hunting strategy. Their diet became much more diverse, including smaller mammals, nimble deer, elk, wild boar, as well as numerous rodents and birds. But hunting such prey required a completely different approach. Heavy spears, effective against the lumbering mammoth, proved useless against the swift deer. They were replaced by lighter and more maneuverable javelins, spears, and a brilliant invention, the spear thrower, which allowed spears to be thrown with tremendous force and accuracy. The crowning achievement of this technological advancement was the bow and arrow, a weapon capable of striking fast game from a distance. Other methods also developed simultaneously. Humans began to actively use traps and snares to capture small animals, tactics that were ineffective against the giants of the past, but ideally suited to the new conditions. Another crucial area of adaptation was the development of water resources. Melting glaciers gave the world a huge number of new rivers, lakes, and coastal areas literally teeming with life. People quickly recognized the potential of these new ecosystems. Fishing became a major food source. This led to an explosion of ingenuity. Specialized tools such as bone fishhooks, braided nets, and barbed harpoons were developed. In coastal areas, people discovered an inexhaustible source of protein: mollusks. Archaeologists are finding huge piles of discarded shells, testifying to the intensive use our ancestors made of this gift of the sea. The emergence of stable food sources near water led to another revolutionary change. Humans adopted a more sedentary lifestyle. They could remain in one place for months without fear of depleting resources. This was a stark contrast to the nomadic lifestyle of megafauna hunters, who were forced to constantly follow migrating herds. But it wasn't only the animal kingdom that became a source of support for humans. As the climate warmed, forests expanded, and plant life became incredibly rich. Gathering transformed from a secondary activity into a crucial part of the survival strategy. People gained access to a huge variety of edible plants, nutritious roots and tubers, juicy berries, and calorie-rich nuts and seeds. This required new knowledge. They needed to understand when and where certain plants ripened, and how to properly harvest and process them. Once again, technology came to the rescue. Stone graters for crushing seeds and wicker baskets for harvesting came into use. A plant-based diet made nutrition more stable and varied, reducing the critical dependence on luck in the hunt. These changes in lifestyle inevitably affected social structure. While small, permanently nomadic groups were the norm during the Ice Age, the diversity of resources now allowed for the creation of larger, more stable communities. Seasonal or even semi-permanent camps emerged. During periods of plenty, for example, during salmon spawning or nut harvests, different groups could gather together to form large settlements. And in times of famine, they would disintegrate again into smaller family units. We see camps becoming increasingly larger and more complex, sometimes even showing signs of permanent structures. This, in turn, contributed to the development of more complex social relations, increased population density, and possibly the emergence of the first trade networks for the exchange of raw materials and finished goods. The need to adapt to a new world became a powerful driver of technological progress. In addition to weapons for hunting and fishing, people created a variety of tools for processing plants and tanning hides. New types of clothing, lighter and more suitable for warmer climates, appeared, as did a variety of housing styles. But one of the most brilliant achievements of that era was microlithic technology. Imagine tiny stone inlays, crafted with precision and possessing a perfect geometric shape. These miniature blades, or microliths, were used to create composite tools, true marvels of ancient engineering. They were inserted into grooves on bone or wooden bases, creating incredibly sharp serrated arrowheads, knife blades, or even sickles for harvesting. These versatile and economical tools became a symbol of a new era. Thus, the end of the Ice Age was not an end, but a beginning. The transformation of landscapes and wildlife forced humanity to display marvels of ingenuity. As they adapted to the new environment, our ancestors' toolkits became increasingly complex, diverse, and efficient. This era, known as the Mesolithic in the Old World and the Archaic period in the New, was a time of astonishing technological advancement that went far beyond conventional notions of the Stone Age. And at the center of this revolution was microlithic technology. Don't let their tiny size fool you. Microliths are not just shards of stone, but high-tech components. Imagine tiny, perfectly crafted blades, triangular, crescent, trapezoid,
each no bigger than a fingernail. These miniature components weren't used alone. Ancient craftsmen inserted them into grooves on bone, horn, or wood bases, creating something entirely new: composite weapons and tools. They were used to create incredibly sharp, serrated spearheads and arrowheads, as well as cutting edges for knives and sickles. The main advantage of microliths was their phenomenal efficiency. Dozens of these sharp blades could be crafted from a single piece of flint, making their production extremely cost-effective. And if one of the blades broke in battle or during work, it could be easily replaced without throwing away the entire tool. It was a truly brilliant decision. Let's travel back to an era of great change, when the very face of the planet was changing before our distant ancestors' eyes.
The glaciers were retreating, and in their place, a new world was emerging, full of new challenges and opportunities. It was at this turning point that human ingenuity revealed itself in all its glory, giving birth to an entire arsenal of specialized tools, perfectly tailored to specific tasks. Imagine rivers growing fuller, lakes overflowing, and seashores coming alive. Water, once an icy barrier, now became an inexhaustible source of food. And to harness these gifts, humans needed entirely new technologies. Thus, the ingeniously simple fishhook appeared in the arsenal of ancient hunters and gatherers. The ancient craftsman would take a piece of bone, a deer antler, or even a sturdy shell, and patiently carve it into a deadly weapon, capable of snatching slippery and swift prey from the water. But what if the target was much larger than a typical fish? Here, in coastal waters, true giants emerged, enormous fish, and even marine mammals. Hunting them required more powerful weapons. And they arrived. These were harpoons, carved from the hardest bone or horn, often equipped with serrated tips that dug deep into the victim's flesh. Every such find at ancient human sites is more than just an artifact. It is irrefutable proof of how deeply our ancestors relied on rivers and seas, how water resources became the basis of their diet. What about mass fishing? Time is merciless to fabric and wood, so almost no fishing nets from that era have survived. However, archaeologists have found telling evidence of their existence: small stones with holes drilled into them. These are weights that pulled the net to the bottom, preventing the catch from escaping. Nearby, we find thin bone needles, ideal for weaving and mending these nets. The emergence of such an efficient method of obtaining food revolutionized the world. The ability to fish on an industrial scale, especially during the seasonal spawning season, allowed entire communities to settle in one place. They were no longer eternal nomads and could establish long-term settlements on the fish-rich banks of rivers and seas. But humans didn't live on water alone. The retreating glacier opened up vast territories that were quickly covered with dense forests. And this new green world offered a completely different diet. Gathering replaced the hunt for giants. Women and children in communities became experts in the world of plants, collecting countless seeds, nuts, and nutritious roots. To transform these hard gifts of nature into food, new tools were needed. Grinding stones appeared, massive stone slabs, and smaller handheld millstones. With these, our ancestors ground wild grains and nuts into flour or nutritious paste. These findings directly indicate a shift in diet. It became increasingly rich in plant carbohydrates, which provided energy for life. To reach the succulent tubers and roots hidden deep in the ground, digging sticks, perhaps one of humanity's most ancient tools, were used. They were often weighted with special stones for greater efficiency. Unfortunately, wood is a fragile material, and archaeological evidence of such tools is extremely rare. The same fate befell baskets and wicker boxes, which were absolutely essential for carrying the harvested crop to the campsite. We rarely find their remains, but logic dictates that without them, the complex process of gathering would simply be impossible. Climate and landscape change forever altered the rules of hunting. The age of Ice Age giants was drawing to a close. Mammoths and woolly rhinoceroses were disappearing, replaced in the dense forests by new game, smaller, faster, and more cunning: deer, elk, wild boar. To bring down such animals, the old spear was no longer enough. Then came the emergence of a technology that would change the rules of the game forever: the bow and arrow. This weapon offered incredible advantages. It had a longer range, was more accurate, and was much more useful in dense forests, where there was no room to swing a spear. Hunters could strike their targets from a safe distance, remaining undetected. This revolution in hunting is also reflected in archaeological finds. We see scatterings of miniature, skillfully crafted arrowheads, often made from tiny stone flakes called microliths. At the same time, tools for processing hides and sewing clothing continued to improve. As people explored new, colder, or conversely, hotter regions, they needed high-quality protection from the elements. Bone and tusk, needles became ever thinner and more elegant. Now, they could be used not only to sew together pieces of hide, but to create complex, tailored clothing that provided ideal thermal insulation, or conversely, ventilation, depending on the weather. Indispensable in this production process were also trusty scrapers for cleaning hides and sharp stone or bone pins used to make holes for sewing. But humans wouldn't be humans if they thought only about survival. This era witnessed a true flourishing of symbolic thinking and art. Craftsmen began to use special chisels called burins, which they used to carve complex designs onto bone, antler, or soft stone. These engravings could be works of pocket art, or even unique recording systems or calendars. People began to adorn themselves. We find beads and pendants made from a wide variety of materials: shells, animal teeth, amber. This means they had tools for drilling tiny holes, polishing, and shaping these first pieces of jewelry. Let's look at the big picture. All technological evolution at the end of the Ice Age was moving toward greater efficiency, versatility, and, most importantly, specialization. Tools designed for a single specific task emerged, and precious raw materials were used much more economically. This was no accident. It was a direct and ingenious response by our ancestors to the radically changing conditions of the world around them. This technological flexibility allowed humanity not only to survive, but to thrive in a new world where there was no longer room for the giants of the past. It was here, on the ruins of the old Ice Age, that the foundations for the future emergence of agriculture and the birth of civilizations were laid. The ingenuity we see in each of these ancient tools is the best testimony to the incredible capacity of the human mind to adapt and solve the most complex problems posed by a wild and unpredictable planet. They acted in coordinated groups, employing cunning strategies such as driving their gigantic prey into natural traps or throwing them off high cliffs. This astonishing ability to plan and exploit the landscape became the key to survival in the icy world of the Ice Age. It was precisely their collective intelligence and the development of increasingly sophisticated tools that allowed ancient humans to challenge even the most colossal giants of the era. The relationship between humans and megafauna is an incredibly complex story, one that still sparks fierce debate among scientists about the precise role our ancestors played in the great extinction that ended the Ice Age. However, one thing is certain: humans emerged as a new, formidable force in the food chain. They began to directly compete with other great predators and, remarkably, often emerged victorious in this brutal struggle for resources. This fragile and constantly shifting balance between hunter and prey was the hallmark of the Ice Age world, a world where brute force and primal survival instincts reigned, forcing both predators and their prey to fight for every passing day. When we hear the phrase prehistoric forests, our imagination conjures up images of dense, warm, and vibrant jungles. But the Ice Age forests were quite different. The plant life of that era was completely subjugated to the cold. The harsh climate created unique natural zones dominated by only those species that could adapt to the permafrost. 3 great plant kingdoms ruled the planet at that time: the tundra, the taiga, and the vast cold steppes known as the Mammoth Prairies. And it was these plant communities that provided the foundation that supported the incredibly rich diversity of animal life of that era. The tundra was the most widespread ecosystem, stretching across all regions bordering the giant ice sheets and occupying vast territories at high latitudes. Its main characteristic was the complete absence of trees. This was due to permafrost, a layer of frozen ground that, like concrete, prevented tree roots from penetrating. Only during the short, cool summer did the topsoil thaw, allowing low-growing vegetation to emerge. The tundra was home to primarily mosses, lichens, sedges, grasses, and dwarf shrubs such as the polar willow. Only the most resilient plants, such as the dwarf willow and dwarf birch, survived these harsh conditions. They developed astonishing mechanisms for surviving in a world of low temperatures. Their low stature protected them from the piercing, icy winds and allowed them to overwinter under a warm blanket of snow. Moreover, their life cycle was incredibly short, to be completed during the short northern summer. And shallow routes were the only viable option, as breaking through the thick ice underground was impossible. Although at first glance the tundra might appear to be a lifeless desert, it was in fact a vital food source for a multitude of animals. This ecosystem provided food for reindeer, mighty musk oxen, and tiny lemmings, herbivores perfectly adapted to life in the cold. The tundra was a surprisingly resilient ecosystem, capable of supporting a remarkable diversity of life in the most extreme conditions. South of the tundra, where the climate was slightly less harsh, lay the boreal forests, which we now know as the taiga. This biome was defined by the dominance of coniferous trees, which were perfectly adapted to the local conditions. Various species of spruce, fir, pine, and larch dominated these cold forests. These warrior trees had their own secrets to survival. Their needle-like leaves helped reduce the evaporation of precious moisture, and their waxy coating protected them from deadly frosts. Their conical shape is not just beautiful, but a brilliant engineering solution, allowing them to easily shed tons of snow without breaking their branches under the weight. Boreal forests served as a vital refuge and food source for many animals, serving as a transition zone between the open tundra and warmer regions. Although the ancient taiga was not as extensive as it is today, patches of it existed wherever conditions permitted, for example, in wind-protected valleys or on low slopes. But perhaps the most significant and widespread type of Ice Age vegetation was the cold grasslands, often called the mammoth steppe. This biome was a vast, treeless expanse that covered much of Eurasia and North America, analogous to modern steppes. But with one crucial difference. Where today we see dense forests or deserts, during the age of mammoths, there were surprisingly fertile and rich grasslands. Various species of grasses, sedges, and herbaceous flowering plants predominated here. Unlike modern grasslands, the vegetation of the mammoth steppe was ideally adapted to cold and arid conditions, growing on frozen soil. The incredible productivity of these grasslands, even in the perpetual cold, was vital for supporting gigantic populations of large herbivores. Among them were woolly mammoths, steppe bison, wild horses, and woolly rhinoceroses. These animals, in turn, created their own world. By constantly grazing and trampling the grass, they prevented the growth of trees and shrubs, maintaining the existence of the steppe biome. The mammoth steppe was a unique ecosystem, unlike any existing on Earth today. When this vegetation disappeared at the end of the Ice Age, it coincided with the extinction of many giant animals whose lives depended entirely on it. Of course, there were other, more localized zones. In valleys and along riverbanks, where there was more moisture and milder temperatures, other types of vegetation developed. So-called gallery forests, or patches of deciduous trees, could grow here, providing refuge for species less adapted to the open, cold climate. These vegetation zones were incredibly dynamic. They constantly shifted north and south, following the advancing and retreating glaciers and responding to the slightest changes in global temperature. But how can we know this after tens of thousands of years? The answer lies in paleontological methods. Analysis of pollen fossilized and preserved in lake sediments, bogs, and ice cores provides invaluable information about past vegetation. By studying these microscopic particles, scientists can pinpoint the exact plant species that grew in a given region thousands of years ago. Macroscopic fossils, preserved leaves, seeds, and wood fragments provide direct evidence of these plants' existence. Furthermore, analysis of the fossilized stomach contents of herbivores, perfectly preserved in permafrost, allows us to glimpse their diet and learn exactly what plants they ate. All these lines of evidence paint a picture of a world in which plant life, though very different from modern life, was incredibly resilient and formed a complex, thriving ecosystem. An ecosystem that supported a huge diversity of animal life, from the tiniest insects to the gigantic megafauna. It was the unique characteristics of these ancient plant communities that became key to the development, survival, and success of the entire Ice Age world. Human evolution. The Ice Age wasn't just a time of giant animals and vast ice sheets. It was a crucial stage in the history of our own evolution. This harsh world witnessed the emergence and development of early human groups who not only survived, but thrived in these unimaginable conditions. In those distant times, two distinct human populations existed on the planet: Neanderthals and early modern humans, known as Cro-Magnons. Their lives became a shining example of human ingenuity and resilience in the face of extreme cold and persistent resource scarcity. Neanderthals, members of the species Homo neanderthalensis, inhabited vast swathes of Eurasia from Western Europe to Central Asia and the Middle East. This extinct human species appeared around 400,000 years ago and disappeared approximately 40,000 years ago. They lived in Europe around the same time as our direct ancestors began to appear there. Neanderthals were distinguished by an incredibly robust build, even more powerful than that of modern humans. They had shorter, stockier limbs, a broad chest, and bulging muscles. All these features were ideal adaptations for conserving heat in cold conditions. This is a clear example of Bergmann's rule, which states that in cold climates, large body size is advantageous because the surface area to volume ratio decreases and heat is lost more slowly. Neanderthal skulls were elongated, with massive brow ridges and a large nose, which may have served as a natural radiator, warming and moistening the icy, dry air they breathed. Their brains were, on average, even slightly larger than those of modern humans, although their structure was likely different. Neanderthals were highly skilled hunters, specializing in the largest game: woolly mammoths, woolly rhinoceroses, bison, and reindeer. Their tactics were deadly. They attacked giants at close range, relying on their physical strength and heavy spears, which exposed them to enormous risks. A study of their skeletons confirms this picture. The bones of Neanderthals are riddled with numerous fractures, remarkably similar to those suffered by modern rodeo riders, evidence of brutal and intense fights with giant animals. They lived in small but highly mobile groups, often finding shelter in caves or under rock overhangs, as well as building temporary dwellings in open spaces. Their diet consisted primarily of meat, but they also gathered plants, fruits, and nuts when available. There is compelling evidence that Neanderthals cared for their sick and wounded relatives and performed deliberate burials of the dead. This already speaks to a high level of compassion and symbolic thinking. Imagine the technological world of the Neanderthals. Their stone tools, while enabling survival, were rather simple and monotonous, lacking the sophistication and diversity we will see in their successors. However, they wielded the greatest power of the era: fire. A flame in a cave was more than just a source of heat. It was a shield against nocturnal predators, a way to make tough meat edible, and the center of their social life. Meanwhile, in the hot savannas of Africa, around 300,000 years ago, a new player entered the scene: Homo sapiens, or Homo sapiens. They had long honed their skills on their native continent, but then a great exodus began. The most powerful wave of migration poured out of Africa approximately 60,000, 70,000 years ago. Wave after wave of these new people spread across the planet, and finally, around 45,000 years ago, they reached Europe, land that had been home to Neanderthals for thousands of years.
Let's put them side by side and see. Physically, they were two different worlds.
The newcomers from Africa, our direct ancestors, were taller, their physique more graceful. Neanderthals had massive bones, and their faces were large and prominent, while Homo sapiens had a lighter skeleton. Their body proportions were ideal for long treks across open terrain and efficient cooling, a clear legacy of their African homeland. But it wasn't just their bodies. Their minds, their social structure, were structured differently. The Cro-Magnons, the name given to the first modern humans discovered in Europe, brought with them a cultural revolution. They created not just capes from animal skins, but actual tailored clothing that provided far better protection from the freezing wind. Their brains, while no larger than those of Neanderthals, appear to have functioned differently. Scientists speculate that the internal architecture of their neural circuits was more complex, unlocking entirely new cognitive advances. The arrival of the Cro-Magnons in Europe signaled the beginning of a new era, an era of incredible technological and cultural advances. Their hunting weapons were an order of magnitude more sophisticated. Instead of heavy spears for close combat, they created light and deadly throwing javelins, and later the pinnacle of prehistoric engineering, the bow and arrow. Their toolbox was full of wonders: razor-thin blades, wood engraving tools, and a host of specialized tools made from bone, antler, and mammoth tusks. These advanced technologies allowed them to become the most effective hunters on the planet, capable of harvesting a wide variety of game and exploiting nature's resources to the fullest. These new humans built complex societies, established trade networks that stretched for hundreds of kilometers, and developed a rich symbolic world. This is evident everywhere, in their elaborate dwellings, cave paintings, exquisite personal adornments, and elaborate funerary rituals. While Neanderthals typically made do with local stone, Cro-Magnons were willing to undertake long expeditions to quarries for high-quality flint. This speaks to an incredible level of planning, logistics, and perhaps even genuine trade. For several thousand years, two human races coexisted in glacial Europe: the stocky, powerful Neanderthals and the tall, resourceful Homo sapiens. This time is one of paleontology's greatest mysteries. What happened when they met? Was it war, trade, or something else? Genetics provides a shocking answer. They not only met, they interbred. Most modern humans of non-African descent carry a drop of Neanderthal blood in their DNA, a living echo of those distant encounters. But why did the Neanderthals disappear? Their demise was likely a tragedy caused by a complex combination of factors. The climate became increasingly harsh. Competition with newcomers for hunting grounds and food intensified. Perhaps the Neanderthals reproduced more slowly or became vulnerable to new diseases brought from Africa. Most likely, all these blows of fate, dealt simultaneously, led to the decline of their civilization. Yet both Neanderthals and our direct ancestors were true masters of survival, demonstrating remarkable adaptation to the harsh world of the Ice Age. They were ingenious hunters and gatherers, skilled in building sturdy shelters and crafting tools that helped them survive in places seemingly impossible to live. Their very presence in these vast, ice-bound expanses is a testament to the incredible resilience and ingenuity of ancient humans. Neanderthals roamed in small, tightly knit groups, following migrating herds of animals or moving in search of edible plants. Their lives depended entirely on a profound understanding of nature, the habits of animals, and the changing seasons. Stone Age people, living in the grip of glaciation, were master craftsmen. They possessed an encyclopedic knowledge of the properties of stone, wood, and bone, and knew how to shape these materials into perfect tools. These skills, passed down from father to son, from mother to daughter, were the thread that bound generations and allowed their culture to survive in a world that demanded constant struggle and innovation. The Ice Age became the greatest test, the crucible in which the very traits that today define us as a species were forged. Survival in that harsh era was unthinkable without the ability to create and use tools. These tools, which we call Stone Age tools, were more than just sharpened stones. They were the fruits of complex technologies perfected over hundreds of thousands of years. They allowed people to hunt giant animals, butcher carcasses, process hides, and create everything they needed to survive in that merciless world. What materials did they have at their disposal? Ancient humans, like any good craftsman, chose what was readily available and had the desired properties. The main resources were stone, bone, antler, and of course, wood. Stone was the alpha and omega of their technology. Ancient craftsmen sought out special rocks that would split predictably upon impact, creating cutting edges sharper than a surgeon's scalpel. Flint and quartz were particularly prized for their fine-grained structure, which allowed for complete control over the cutting process. And where volcanoes erupted, people found a true treasure: obsidian, a volcanic glass. Although brittle, its edges were so sharp they rivaled modern blades. The primary technique for working flint was called flint chipping, or simply flint knapping. Imagine a craftsman holding a core, a chunk of stone, in one hand and a hammer, a second stone, in the other. With a precise, controlled blow, he breaks a thin flake from the core. Sometimes, instead of a stone hammer, a softer material, a piece of deer antler or hardwood, was used. This allowed for thinner, more precise flakes, creating either a sharp edge on the core itself or ready-to-use blanks. The oldest and most durable tool, a true Swiss army knife of the Stone Age, was the hand axe, or axe. These double-ended, teardrop-shaped tools were incredibly versatile. They could chop wood, dig up edible roots, and, of course, butcher the carcasses of slain giants like mammoths and woolly rhinoceroses. Its shape was perfectly designed to fit comfortably in the palm of the hand. Over the millennia, axes became increasingly elegant, symmetrical, and sharp. But then a technological revolution occurred. The emphasis shifted from massive tools forged from a single piece of stone to lighter and more efficient tools made from flakes. Now, sharp blades chipped from a core became the primary tools themselves. This was a breakthrough in efficiency. Dozens of razor-sharp tools could now be made from a single piece of flint. Among these new tools, scrapers occupied a special place. These were flakes with one or more edges deliberately blunted for ease of grip, while the opposite edge was carefully sharpened. Their main purpose was to process hides. Using scrapers, they scraped away the remaining meat and fat, preparing the skin for further processing. It was this unassuming tool that made the hides soft and supple, turning them into warm clothing, shelter material, and durable bags. The ability to create windproof and warm clothing was a matter of life and death in the icy hell of the Pleistocene. The next step in evolution was the invention of blades. A blade is a special flake, at least twice as long as it is wide, with perfectly smooth, parallel edges. Their creation required the highest level of skill and specialized techniques, whereby the craftsman could flake blade after blade from a single prepared core, as if on an assembly line. These blades produced a long and incredibly sharp cutting edge, making them far more effective than any previous tools. They could serve as butcher knives or as blanks for the creation of even more complex, specialized tools. Arrowheads were especially important for hunting. These were skillfully crafted stone slabs, most often triangular or leaf-shaped. Their purpose was to act as a deadly sting at the end of a spear or dart. The earliest arrowheads were simple, but later, true technological breakthroughs emerged, such as the spear thrower or atlatl. This simple device, acting as a lever, greatly increased the range and killing power of a throw. And towards the end of the Ice Age, with the invention of the bow, tiny, finely crafted arrowheads appeared, allowing for precision hunting from great distances. But ancient humans didn't live by stone alone. The use of organic materials was an integral part of their world. Animal bones and horns were invaluable resources, capable of crafting strong and delicate tools impossible to make from stone. Awls, sharpened bone tools, were used to puncture skins for sewing. and needles often made from bone or mammoth ivory, with a tiny drilled eye, allowed for the creation of intricate, tailored clothing, vital in cold climates. Harpoons with barbed tips for catching large fish were also carved from bone and antler. All these finds demonstrate the profound understanding of ancient people's properties of a wide variety of materials. Although wood rarely survives in the ground for tens of thousands of years, it was undoubtedly one of the most important materials of antiquity. It was used to make axe handles, spear and arrow shafts, shelter frames, and countless other essential household items. Imagine that distant and harsh time. Wooden spears, with their fire-baked and sharpened ends, were almost certainly among the very first hunting weapons, allowing humans to challenge mighty beasts. But wood wasn't just for hunting. It was used to make simple digging sticks for finding edible roots, to create sturdy handles for heavy stone axes and scrapers, and to assemble frames for primitive shelters that provided protection from the icy wind. Of course, wood is a short-lived material, and time has swallowed most of these artifacts, leaving us with only conjecture. And although it was a vital part of Stone Age technology, our understanding of its role is much more hazy than that of stone or bone, which have survived millennia. The evolution of tools we observe throughout the Ice Age is not just a history of technology. It's a history of the development of the human mind itself, its increasing sophistication, and incredible adaptability. Initially, tools were incredibly simple, crude, and versatile, suitable for a multitude of tasks. But as hundreds of thousands of years passed, they were replaced by increasingly sophisticated and specialized tools. Their creation required not only manual dexterity, but also profound planning and the ability to foresee the future. This astonishing progress can be traced step by step, from Acheulean hand axes to Mousterian flakes, and then to the elegant blades and tiny microliths of the Upper Paleolithic. Each new technology is evidence of the relentless refinement of processing techniques and an ever-deepening understanding of the properties of materials. The ability to consistently create sharp and effective tools from what lay literally at our feet became the fundamental skill that allowed humans not only to survive, but also to begin their journey to planetary dominance. Ice Age humans were forced to struggle for existence in incredibly harsh and changing conditions, and it was tools that became the key to their prosperity. Tools were more than just objects. They became extensions of the human hand, intellect, and will, allowing our ancestors to conquer a hostile environment and carve out their place in the harsh world of the Ice Age. However, one of the most incredible and captivating legacies of that era is cave art. Just think. In the pitch-black darkness of deep caves across Europe and beyond, astonishing paintings, engravings, and even sculptures have been discovered. This ancient art is like a window into the consciousness, beliefs, and world of our ancestors. It demonstrates a level of artistic talent and symbolic thinking that continues to inspire awe and admiration in researchers today. And these aren't just random drawings on walls. These are complex, thoughtful compositions, often found in the most inaccessible and dark corners of caves, indicating their colossal, perhaps sacred, significance for ancient people. The most impressive Ice Age galleries are located in Western Europe, primarily in what is now France and Spain. Among these underground treasure troves, the Lascaux and Chauvet caves in France, as well as Altamira in Spain, stand out. Imagine the Chauvet cave, discovered only in 1994. Its depths conceal some of the most ancient cave paintings, estimated to be 32,000 talon, 37,000 years old. The famous Lascaux cave, discovered in 1940, reveals stunningly dynamic and beautiful works created approximately 17,000 years ago. And the history of the Altamira cave, with its legendary bison-painted ceiling, spans approximately 14,000 years. These and dozens of similar sites demonstrate an unbroken artistic tradition that has existed and evolved over tens of thousands of years. What did these ancient masters depict? Primarily, it was the animal world, the world of the mighty megafauna that surrounded them. The entire Ice Age fauna comes to life on the cave walls. We see majestic, woolly mammoths, mighty bison, both European and steep, graceful horses with lush manes and armored woolly rhinoceroses. Herds of reindeer graze here, and formidable predators, cave lions and giant cave bears, lurk nearby. And what's striking is the incredible anatomical precision with which they are depicted. Artists of that era sought to convey not just the animal's appearance, but also the very sense of movement, its vitality and power. One of the most ingenious features of these drawings is how masterfully the ancient masters utilized the natural curves and protrusions of the rock walls to give their creations volume, creating a stunning three-dimensional effect. It seems as if the animals are about to emerge from the walls and move straight toward you. But against this backdrop of animal splendor, human figures are extremely rare. And when they do appear, they are depicted very roughly, schematically, and sometimes even as mysterious hybrids, half human, half beast. Furthermore, the cave walls are covered with abstract symbols. Dots, lines, geometric patterns. The meaning of these symbols remains one of the greatest mysteries of the Paleolithic. One of the most common and personal motifs are handprints, made using a stencil technique. A person pressed their hand against the wall and sprayed pigment around it. Artists sourced their paints directly from under their feet. Red, yellow, and brown hues were obtained from ochre, a mineral rich in iron oxide. Black was produced from charcoal or manganese dioxide. White paint was sometimes made from kaolin clay. These minerals were carefully ground into a fine powder and then mixed with binders, animal fat, blood, or simply water to produce a thick paint. It was applied in a variety of ways. Some drawings appear to have been made simply with fingers or pieces of moss. For others, brushes made of animal hair or plant fibers were used. A very common technique was spraying. Dry pigment was blown through a hollow bone or reed tube. This allowed for smooth contours and the coverage of large surfaces, producing an effect similar to a modern airbrush. Engravings were simply scratched into the soft rock surface with a sharp stone chisel. In some caves, archaeologists have even found traces of primitive scaffolding or ladders. This suggests that the artists worked at great heights, right under the ceilings, which required tremendous effort and careful planning. But why? Why did they do all this? This question remains the subject of heated debate among scholars. There is no single answer, and most likely, the art served several functions. One of the most popular theories is that it had a magical, ritualistic purpose. Perhaps the drawings served to protect the tribe or to attract good luck. Images of animals pierced by spears could have been part of a ritual designed to ensure success on a real hunt. This is so-called sympathetic magic, the belief that influencing an image can influence the real object. According to another hypothesis, cave paintings were part of initiation rites, dedicating young men to the ranks of hunters. Or they served as visual aids for transmitting knowledge about animal habits and hunting tactics from older to younger generations. Some researchers see these images as a reflection of shamanic practices. Perhaps shamans, in a trance, traveled to the spirit world, and the paintings on the walls are frozen images of their visions. Other interpretations suggest that art was a means of storytelling, a record of important events, myths, or family histories. Abstract symbols could represent complex concepts, serve as star maps, or even a locale. Or perhaps it was simpler and merely an expression of aesthetic sensibility, the desire of ancient people to embellish their world and express their creative impulse. The very location of these galleries in dark, hidden parts of the caves hints at their sacred nature. They were not intended for public display. The presence of handprints and repeating symbols may indicate a kind of signature, a sign of belonging to a particular clan or lineage. But regardless of its true purpose, rock art silently tells us a great deal about the lives, beliefs, and world of Ice Age people. It demonstrates their incredible powers of observation, their profound knowledge of the habits of the animals with whom they lived side by side. This art proves that animals were more than just a source of food for them, but central figures in their cosmology and mythology. It speaks to the capacity of our distant ancestors for abstract thought and the creation of complex symbolic systems.
The sheer effort expended in creating these masterpieces, the mining and preparation of pigments, the risky journey through the dark labyrinths of caves, the actual work on the intricate designs, all testifies to a highly developed culture, one in which there already existed a division of roles and shared lofty goals. Cave art is irrefutable proof of the intellectual and creative power of our ancestors. It proves that even in the harshest conditions of the Ice Age, the human spirit irrepressibly strove to express itself, to make sense of the world around it, and to leave its mark on eternity. During the Ice Age, ancient humans, whether Neanderthals or early Homo sapiens, organized their lives in settlements of all types, from tiny, temporary hunting camps to more permanent base camps.
People often established temporary camps that could be used for anything from a few days to several seasons, depending on animal migration, resource availability, and cultural traditions. These camps were the heart of their daily lives, providing shelter from the elements, a place to make and store tools, prepare food, and, of course, socialize. Understanding how these ancient communities built and used their dwellings allows us to truly appreciate the resilience and ingenuity of our ancestors in those harsh conditions. Shelter types varied greatly depending on the terrain and available materials. In regions with abundant rock, people naturally often used natural caves and rock overhangs. Let's step back into the harsh world of the Ice Age, where survival was a daily struggle. In this world full of dangers, natural shelters like caves were a true godsend. Their stone vaults provided a reliable shield from piercing winds, freezing rains, and relentless snowstorms, while their depths maintained a more or less constant temperature. But don't think that ancient people simply settled in bare rock. No, within these natural fortresses, they created their own cozy haven. Using the skins of slaughtered animals, sturdy branches, and even mammoth bones, they erected additional barriers from the wind and built sleeping platforms raised above the cold ground. Imagine the scene uncovered by archaeologists in European caves. Here, in the semi-darkness, are the neat holes left by pillars that once supported hide tents, and there, the remains of an ancient hearth around which families gathered. This tells us that the living space was carefully planned and organized. The fact that some caves were used by people for generations, sometimes even millennia, made these places more than just homes. They became family nests, important centers for entire tribes roaming the vast expanses of the ancient earth. But what do you do when there's not a single rock for hundreds of kilometers? On the open plains, especially in the vast steppes of Eastern Europe and Siberia, shelter was extremely scarce. And here, our ancestors demonstrated incredible ingenuity. They learned to build shelters from what was abundant, the remains of Ice Age giants, primarily the bones of mighty mammoths. At sites like the famous Mezherych in modern-day Ukraine, we encounter true architectural marvels. These round or oval structures, the walls of which are composed of dozens, sometimes hundreds, of mammoth skulls, massive femurs, and pelvic bones. These bones were skillfully fitted together, forming a strong and reliable framework. Such a bone house was likely covered with enormous mammoth or reindeer skins, creating a warm, protected interior. Just imagine the level of organization and teamwork required to collect, transport, and stack such a colossal number of bones. Some of these structures were particularly large. Inside, archaeologists have found traces of multiple hearths. This may indicate that either several families lived here simultaneously, or the space was divided into different zones. And although these bone huts were temporary shelters, they served as reliable seasonal camps where one could live in relative comfort for several weeks, even months. Of course, other materials, such as wood, were also used for construction. However, wood is a fragile material, and only indirect evidence of such structures has survived to this day. At some ancient sites, scientists have discovered circular post holes. This is a clear indication that structures made of wooden poles once stood there, likely also covered with hides or dense shrubs. Such camps were usually set up near water sources. The bones of smaller animals, such as reindeer antlers, were also used. They were always readily available and were used for a variety of simpler, more utilitarian tasks. The lives of ancient people were subject to constant movement. Due to their nomadic lifestyle, their shelters often had to be erected and dismantled on short notice. Therefore, they had to be easy to assemble, allowing them to be quickly built or moved to a new location when needed. The entire existence of these early human communities revolved around basic instincts: finding food, staying warm, and protecting themselves from predators that roamed everywhere. Their society likely already had a clear division of responsibilities. Men, united in hunting parties, would go out in search of prey, while other tribe members gathered edible plants, prepared food, made tools, and maintained order in the camp. Imagine a hunting party heading out into the wilderness for several days to track and bring down a huge animal. After a successful hunt, a true celebration would begin in camp. The carcass would be butchered communally, and the entire tribe could finally enjoy the taste of fresh, nutritious meat. For efficient butchering, specialized stone tools with razor-sharp edges were used. Some of the meat was eaten immediately, while the rest was dried or smoked to preserve for later use. The hides of slaughtered animals were carefully processed. They were cleaned and kneaded with scrapers, and perhaps even with the animal's brain, turning them into a soft and durable material for clothing, warm blankets, and shelter coverings. Bones and antlers were used to craft not only tools and weapons, but also the first jewelry, which spoke of a nascent sense of beauty. The heart of any camp, its beating pulse, was fire. The hearth was a symbol of life itself. It was carefully constructed and tirelessly maintained, providing warmth on icy nights, light in the pitch darkness, the ability to cook hot food, and, of course, protection from predators who feared the flames. The presence of multiple hearths in large camps suggests that different families likely gathered around their own fires. This created a remarkable balance: on the one hand, a sense of community, and on the other, the preservation of privacy for each family. Cooking food over fire was a vital process. Not only did it enhance the taste of food, but it also broke down tough fibers, making meat and plants more nutritious and digestible. Heat treatment made food safer and more accessible to the body. But fire wasn't just for cooking. It was used, for example, to temper wooden spearheads, making them hard and deadly, or to process other materials. We can infer the social organization of ancient humans from archaeological evidence and by drawing analogies with modern hunter-gatherer tribes. Groups were likely small, consisting of several related families, perhaps 25 to 50 people. This size was ideal for effective cooperative hunting and resource sharing without depleting the environment. Important decisions were likely made collectively by the entire tribe or by a council of the most respected elders. Sharing spoils, especially after a large game hunt, was more than just a matter of dividing up food. It was a crucial social ritual that strengthened bonds within the group and ensured the survival of the entire group. Even those unable to hunt, the sick, the wounded, or the elderly, were not left without support and received their share. There is compelling evidence that the elderly and those with disabilities were given special care. The famous discovery of a Neanderthal from La Chapelle-aux-Saints, who lived to a ripe old age suffering from severe arthritis and having lost almost all his teeth, vividly demonstrates the profound sense of community and compassion inherent in our distant ancestors. The camp was more than just a place to sleep and eat. It was a center for the transmission of invaluable knowledge. It was here, among fellow tribesmen, that young people learned the skills necessary for survival: how to properly craft a stone axe, how to read tracks in the ground, how to understand animal habits, and how to navigate the terrain. Sharing stories and experiences around the evening campfire was vital for preserving culture and passing on wisdom from one generation to the next. The presence of personal adornments, such as shell beads or tusk pendants, as well as the appearance of the first rock paintings near the sites, speaks volumes.
This means that the harsh conditions of the Ice Age provided space for creativity, symbolic rituals, and the development of a complex cultural identity. These settlements were more than just shelters. They were living, breathing social centers where the very foundations of human civilization were forged amid the harsh conditions of the Ice Age. During that period, the planet itself looked completely different.
Gigantic ice sheets, several kilometers thick, encased a vast portion of the northern hemisphere. These glaciers held so much water that sea levels dropped by more than 100 meters. This led to a remarkable phenomenon. Vast tracts of continental shelf, now hidden underwater, became exposed and became dry land. Thus, natural land bridges emerged, connecting continents that are now separated by seas and oceans. These bridges became vital highways, enabling animals, plants, and, most importantly, for our history, groups of ancient humans to travel vast distances and populate new lands. The most famous and grandiose of these land bridges was Beringia. This colossal landmass connected Northeast Asia, or Siberia, with northwestern North America, or Alaska. Today, these two continents are separated by the Bering Strait. But during the last glacial maximum, approximately 26,000 years ago, when sea levels were at their lowest, Beringia was a vast ice-free landmass. At its widest point, it could have been up to 1,500 kilometers wide. This wasn't just a narrow isthmus, but an entire country with its own unique ecosystem. Due to its geographic location, Beringia remained virtually ice-free, as the giant ice sheets nearby sucked all the moisture from the atmosphere. A cold but grass-rich steppe, similar to Ice Age tundra, stretched here. This environment provided food for countless herds of large animals, including woolly mammoths, steppe bison, wild horses, and reindeer. Beringia served as a vital migration corridor for these species between Asia and North America. Animals that evolved in Eurasia had the opportunity to migrate to the New World, and vice versa. This great exchange of species incredibly enriched the biodiversity of both continents and facilitated the emergence of new life forms adapted to harsh conditions. For example, the ancestors of modern American bison, horses, and camels originated in Asia and crossed Beringia into North America. Similarly, albeit in smaller numbers, some North American species migrated westward into Asia. But Beringia wasn't the only such bridge. Other land corridors also played a key role in shaping the map of life on the planet. Between mainland Australia and New Guinea, the Sahel Shelf became exposed during periods of low sea levels, forming a single landmass. This bridge became a decisive factor in the early human settlement of Australia, allowing the first humans to migrate from Southeast Asia. A similar story unfolded with the Sunda Shelf, or Sunderland. This land bridge connected mainland Southeast Asia with the modern islands of Sumatra, Borneo, and Java. During ice ages, it was open, facilitating the movement of animals and ancient human populations across what are now island nations. It was these connections that allowed Homo sapiens to spread so early across the islands of Southeast Asia and penetrate into distant Oceania. Another remarkable example is the land connection between the British Isles and continental Europe. Imagine a world where the boundaries between the continents were completely different. Where cold waves rage today, gigantic land corridors once stretched, connecting Britain with the rest of Europe. During the harshest periods of the Ice Ages, sea levels dropped so low that the legendary Bering Isthmus emerged, a bridge between Asia and America, opening the way for great migrations. Take a look at the southern North Sea. In those distant times, it wasn't a flat expanse of water, but a vast, grassy lowland that scientists call Doggerland. This sunken world was a key route for herds of ancient animals and for the first human tribes moving between what would become the British Isles and the mainland. But glaciers don't last forever. As the giant ice caps began to melt, sea levels rose inexorably. Water returned to the oceans, and Doggerland slowly disappeared beneath the waves, turning Britain into an island and creating the English Channel.
The very emergence of these land bridges was directly linked to massive climate cycles. Imagine colossal ice sheets covering a significant portion of the planet. They acted like giant sponges, absorbing unimaginable volumes of water from the world's oceans, leading to catastrophic shallowing.
When warming set in and the glaciers retreated, all this water rushed back into the ocean basins, flooding lowlands and severing land connections between continents. This majestic process repeated itself over and over, meaning that ancient corridors appeared and then disappeared over tens of thousands of years, opening and closing windows of opportunity for migration. The lowest point of the global ocean's decline was reached at the peak of the last ice age. Just imagine. The water level retreated an incredible 100, even 120 meters below today's level. This colossal drop exposed vast tracts of continental shelves across the globe. As a result, in addition to the well-known giants like Beringia, many smaller, but no less important, land bridges emerged. The existence of these temporary bridges was crucial to the entire history of humanity. The legendary Beringia became the central stage in the drama of the peopling of the Americas. It was along this corridor from Asia that not only the first humans arrived to the new unexplored continent, but also their technologies, their culture, and their way of life. For ancient hunter-gatherers, the ability to cross these land routes was a matter of survival. They followed in the footsteps of migrating herds of mammoths and bison, conquering ever-new lands. People, like animals, walked across this land, discovering rich hunting grounds and exploring territories where no human had set foot before. This is how, step by step, the global dispersal of our species across the planet took place. The emergence and disappearance of these land corridors directly influenced migration routes, cultural development, and even the genetic diversity of peoples on different continents. These dynamic bridges didn't just change the map of the world, they channeled the flow of life across the Earth. The history of the initial settlement of the American continents is a true scientific mystery, full of mysteries and debates. The prevailing theory holds that the first modern humans made a great exodus from Asia to North America, crossing that very same land bridge. It was a monumental journey undertaken by intrepid clans of hunters and gatherers at the height of the Ice Age. Their trek led to the settlement of two vast continents, from the Arctic wastes in the north to the southernmost reaches of Patagonia. Traces of these ancient pioneers are found throughout the Americas, right up to its southernmost reaches. Their journey began in the harsh lands of Northeast Asia, most likely in what is now Siberia. There lived tribes of hunters, perfectly adapted to survival in the icy hell. During the peak of the last glaciation, approximately 26,000 to 20,000 years ago, a global drop in sea levels created the vast land bridge connecting Siberia with Alaska. This lost continent, known to us as Beringia, was fortunately not covered in ice. Instead, it was a cold but grazing steppe, an ideal habitat for large animals and, consequently, for the people who hunted them. It is generally accepted that the first groups of settlers followed migrating herds of woolly mammoths, ancient bison, and wild horses. Slowly, generation after generation, they moved across Beringia until they reached the lands of modern-day Alaska. It's important to understand, this wasn't a rapid march. No, it was a saga stretching over many centuries, perhaps even millennia. Entire generations likely lived and died in the vastness of Beringia before their descendants moved further into the American interior. But when exactly did humans first set foot on American soil south of the glaciers? This question still sparks heated debate in the scientific community. For decades, the prevailing theory was the so-called Clovis culture, known for its unique fluted spearheads. It was believed that these people, who lived approximately 13,500 years ago, were the first Americans. However, archaeological discoveries in recent years have completely overturned this picture. Compelling evidence has been found of sites that predate the Clovis culture by far. Sites like Monteverde in Chile, which is at least 14,500 years old, or Paisley Caves in Oregon, where human footprints date back to the same time, provide irrefutable evidence that humans arrived in the Americas much earlier. This means they were already present in North and South America even before the land corridor leading south opened between the giant glaciers. The route from Alaska to the south was once completely blocked by two colossal ice sheets, the Laurentide ice sheet to the east and the Cordilleran ice sheet to the west. This wall of ice, covering most of modern-day Canada, was long considered completely impassable. Scientists believed that ancient people were forced to wait thousands of years for an ice-free passage to form between these two ice sheets. Such a corridor did indeed appear, but only around 14,000 to 13,500 years ago. However, discoveries at older sites south of the glaciers prompted a search for an alternative explanation, and one was found. The first migrants likely used an alternative, far more dangerous route along the coast. This hypothesis, called the coastal migration theory, suggests that early humans moved south along the Pacific coast of North America, possibly on primitive boats or rafts. They moved from one resource-rich area to another, following marine ecosystems that were accessible even when the continent's interior was icebound. This allowed them to bypass the ice barrier and begin settling the continent much earlier. But whatever their precise route, one thing is certain. Once humans found themselves south of the ice sheets, their spread across both American continents was staggeringly rapid. Within just a few thousand years, their campsites appeared at vast distances from one another. These ancient Americans were unrivaled masters of survival, hunter-gatherers capable of adapting to any conditions. They hunted the gigantic megafauna of the Ice Age, colossal mammoths and mastodons, giant sloths, and fearsome saber-toothed cats. Their stone tools and hunting techniques, honed over centuries, were deadly weapons. They also masterfully exploited all available local resources: fish, shellfish, birds, and a vast variety of edible plants. As people spread across North America, new cultural adaptations emerged. Tribes occupied new ecological niches, from the Great Plains to the forested east and the arid southwest. In South America, their expansion was even more rapid. In just 2,000 years, they reached the southernmost tip of the continent, Patagonia. This incredible speed testifies to the extreme mobility of these people, their phenomenal ability to adapt, and their profound understanding of survival strategies. But don't think the journey of the first Americans was a walk in the park. They encountered completely unfamiliar landscapes, new predators, and a constantly changing climate. And yet, their ingenuity, social organization, and technological skills allowed them not only to survive, but also to colonize two vast, previously uninhabited continents. Genetic studies of modern Native Americans fully confirm this story. Their ancestors came from Asia. Genetic diversity steadily decreases from north to south, clearly indicating the direction of expansion. The story of the peopling of the Americas is a gripping saga of exploration, adaptation, and the indomitable human spirit that drives us to discover new worlds, forever changing the face of our planet. What was happening at this time on the other side of the Atlantic, in the Old World? During the last glacial maximum, which lasted from approximately 110,000 odd to 12,000 years ago, Europe presented a completely different spectacle. It was a world encased in ice, shaped by gigantic ice sheets and locked in an extremely cold climate. This era, known as the European Upper Paleolithic, was a time of severe trials and great achievements for our ancestors. Let us step back into the icy world of Europe tens of thousands of years ago. It was an era that became the arena for the flourishing of astonishing human cultures, including both the battle-hardened Neanderthals and the early modern humans who succeeded them. Before us lies a continent transformed into a dynamic, ever-changing icy wasteland, where life was defined not by cities, but by the relentless movement of glaciers and the edges of the endless tundra. At the peak of this glaciation, during a period scientists call the last glacial maximum, approximately 20,000 to 26,000 years ago, northern Europe was buried beneath the colossal Scandinavian ice sheet. Imagine this icy monster. It originated in the mountains of Scandinavia and then, like an inexorable avalanche, began to spread in all directions. It crossed the Baltic Sea, covering all of modern-day Norway, Sweden and Finland, and its icy tongues reached into what is now Denmark, Germany, Poland and Russia. This ice sheet engulfed virtually the entire British Isles, leaving only a few isolated mountain peaks in the south. The thickness of this ice sheet at its center reached several kilometers, and its monstrous weight literally crushed the Earth's crust. As it moved, it plowed the Earth beneath it, carving deep scars into the rocks that we know today as the majestic Norwegian fjords and hollowing out the basins for Finland's thousands of lakes. South of this giant glacier, so-called periglacial conditions prevailed across much of Western and Central Europe. This means that although the land itself was not covered by ice, it was bound by permafrost, frozen to a great depth, hard as stone. The landscape here was treeless tundra and frigid steppes swept by icy winds. Cycles of freezing and thawing formed bizarre patterns and icy hills, pingos on the surface. Even in regions further south, such as the Mediterranean, the climate was much cooler and drier than today. And although the continental glacier never reached here, high-altitude regions like the Alps and Pyrenees gave birth to their own enormous valley glaciers. These climatic upheavals completely transformed the continent's flora. The great forests that once covered Europe shrank and retreated to small refuges in the south. They were replaced by endless meadows and tundra steppes, providing ideal pastures for gigantic herds of prehistoric animals. And it was in this harsh world that humans had to survive, demonstrating miracles of ingenuity. The very first inhabitants of this icy Europe were the Neanderthals. They were perfectly adapted to these conditions, having evolved here for hundreds of thousands of years. Their powerful, stocky build with short limbs and a broad chest was a brilliant natural solution for conserving heat in the bitter cold. Neanderthals were fearless and skilled hunters. Imagine this hunt. They didn't use bows or javelins. Their weapons were heavy spears with stone tips, designed for close-quarters combat. It was a deadly one-on-one encounter, with giants like the woolly mammoth, woolly rhinoceros, or enormous steppe bison. Archaeological finds from sites like La Chapelle-aux-Sens in France tell us astonishing stories of Neanderthals caring for their sick and elderly, suggesting a complex social organization. Their stoneworking technology, known as the Mousterian culture, was incredibly efficient. They created versatile tools for a variety of tasks, from butchering animal carcasses to processing hides for clothing. They often chose natural caves and rock overhangs as their homes, providing reliable shelter from the elements. But around 45,000 years ago, new players entered the scene. Early modern humans, our direct ancestors. Homo sapiens began their great migration out of Africa and the Middle East and arrived in Europe. Their arrival marked the beginning of a new era, the Upper Paleolithic, a time of incredible technological and cultural advances. These people, often called Cro-Magnons, brought with them an entirely new, far more sophisticated toolkit. They learned to make thin, sharp stone blades and mastered the crafting of bone, antler, and mammoth tusks. From these materials, they crafted specialized weapons, such as spearheads and perhaps even arrowheads, as well as eyed bone needles. This seemingly simple invention revolutionized humankind. It made it possible to sew together animal skins, creating warm and comfortable clothing that protected from the cold far more effectively than the primitive capes worn by the Neanderthals. These new inhabitants of Europe were also more sophisticated hunters. They relied not only on brute force, but also on intelligence, developing complex strategies. They organized collective drives and ambushes and developed projectile weapons that allowed them to strike prey from a safe distance. Their diet was much more varied. They hunted not only large game, but also fished, hunted birds, and took small animals, demonstrating incredible flexibility and an ability to utilize all available resources. Their settlements also became more complex. They lived not only in caves, but also built actual dwellings in the open, sometimes using enormous mammoth bones as frames, as was discovered at the Mezhyrich site in Ukraine. But most astonishing is the cultural explosion that occurred during the Upper Paleolithic era. Deep in caves, by the flickering light of torches, these people created true masterpieces. The cave paintings in places like the Lascaux and Chauvet caves in France and Altamira in Spain are breathtaking. Hunting scenes come to life on the walls like a prehistoric movie theater. Herds of bison gallop, wild horses gallop, and predators lurking. These images, created using natural pigments, likely held profound ritual and magical significance. In addition to cave paintings, ancient artists created numerous smaller works of art, skillfully carved ivory and ivory figurines of animals and humans, including the famous Paleolithic Venuses, as well as beads and pendants that suggest the emergence of personal adornment and complex symbolic thought. These people also practiced complex burial rituals, burying their dead with weapons and jewelry, which may indicate a belief in an afterlife. And what about the Neanderthals? For a time, they coexisted with the incoming Homo sapiens. Genetic studies show that interbreeding even occurred between the two species. However, about 40,000 years ago, the Neanderthals disappeared from the face of the Earth forever. The reasons for this extinction are one of the greatest mysteries of paleontology. Most likely, it was a deadly cocktail of various factors: sharp climate fluctuations, competition for resources with more numerous and technologically advanced modern humans, and possibly lower birth rates. At the very end of the Ice Age, nature dealt the final blow, a sharp and severe cold snap known as the Younger Dryas. And yet, despite all the difficulties, the human cultures of Ice Age Europe demonstrated incredible resilience, innovation, and creative genius, laying the foundation for all subsequent development of civilization. Now let's shift our gaze eastward, to the planet's largest continent. The Ice Age manifested itself in vastly different ways in Asia, from the gigantic ice fields of Siberia to the subtle climate shifts in the southern regions. Much of northern Asia during this era was gripped by brutal cold, permafrost, and endless steppes. This vast landmass became a key arena for the evolution and migration of ancient humans, including those intrepid hunters who were the first to cross the Bering Strait and settle the Americas. Northern Asia, and especially Siberia, was located in a periglacial zone. Although there was no continuous ice sheet here, as in Europe, vast expanses were locked in permafrost. Massive glaciers and ice caps formed in mountain ranges such as the Himalayas, Altai, and the Tibetan Plateau. The northern plains of Siberia hosted a unique, now extinct ecosystem known as the Mammoth Steppe. It was a truly lost world of frigid grasslands, stretching from Eastern Europe across Siberia to Mongolia. These steppes were home to countless herds of Ice Age megafauna: woolly mammoths, woolly rhinoceroses, steppe bison, and wild horses, which provided an inexhaustible food source for ancient hunters. The climate here was extremely harsh, with severe frosts, drought, and hurricane-force winds. These winds, sweeping across the treeless plains, raised clouds of dust from the glacial areas and deposited them in a thick layer, creating so-called loess deposits, which today form the most fertile soils in some parts of China. But in Southeast Asia, the picture was different. There was no direct glaciation, but temperatures dropped, and most importantly, sea levels dropped drastically. The exposed seafloor created a gigantic land bridge known as Sunderland. It connected mainland Asia with the modern islands of Sumatra, Borneo, and Java, opening a route for the migration of animals and people. Similarly, to the south, the Sahel Shelf connected Australia and New Guinea, playing a key role in the settlement of the Australian continent. The human presence in Asia during the Ice Age was incredibly diverse and crucial for understanding how our ancestors dispersed across the planet. Modern humans, Homo sapiens, emerged in Asia as a result of several waves of migration from Africa, beginning approximately 60,000 to 70,000 years ago. Slowly but surely, they spread across the vast continent, each time adapting to new, sometimes extreme conditions, from the icy Siberian tundra to the tropical forests of the southeast. Fossil remains and archaeological finds in East Asia confirm this grand story of the exploration of a new world. Imagine our modern understanding of the ancient world collapsing. Imagine transporting ourselves to the icy desert of Siberia. It seems incredible, but even here, in the realm of permafrost, life was thriving 30,000 years ago. Archaeological finds paint a picture of incredible resilience. Our ancestors lived far beyond the Arctic Circle. One such piece of evidence is the massive horn of a woolly rhinoceros discovered on the banks of the Yana River. This artifact is more than just a bone, but proof that humans learned to survive the hell of the Ice Age. They challenged the giants of that era, hunting enormous rhinos and other megafauna. To do this, ancient Siberians developed unique tools and sophisticated hunting tactics that allowed them to prevail in this eternal battle for survival in the extreme cold. It was precisely Asia during the Great Ice Age that became the stage for one of the most monumental events in human history, the colonization of North and South America. As we already know, there existed a gigantic land bridge known as Beringia, which, like a titanic artery, connected Northeast Asia with the lands we now call America. Closely connected to the Alaskan territory, human tribes, hardened by Siberian frosts and the harsh steppe climate, moved east. They did not move blindly. They followed migrating herds of animals across Beringia, colonizing a new, unexplored continent. This great migration stretched over millennia. Some groups may have lingered for long periods on Beringia itself, this lost world, before continuing their journey south, deep into the American interior. Even today, the genetic code of Native Americans preserves the memory of this journey. Analysis of their DNA irrefutably proves a close kinship with the peoples of East Asia, confirming the theory of the Great Migration. Across the vast expanses of Asia, ancient human cultures developed in vastly different ways, each developing unique technologies perfectly suited to their specific conditions. In the windswept steppe regions, nomadic tribes of hunters and gatherers relied on large game. Armed with spear throwers and later more sophisticated weapons like bows and arrows, they stalked herds. Their arsenal included sharp stone blades, deadly spearheads, and scrapers essential for butchering carcasses and processing tough hides. A completely different picture was observed in other corners of the continent. In areas with dense forests and along coastlines rich in seafood, life flowed differently. Diets and toolkits were far more diverse here. And throughout Asia, we find traces of the complex social structures, ritual practices, and symbolic thinking that were the hallmark of that distant era. For example, in different parts of the continent, archaeologists are finding ancient jewelry, beads skillfully crafted from seashells or animal bones, evidence of man's attraction to beauty. But the age of ice couldn't last forever. A turning point had arrived. Rising global temperatures caused the giant ice sheets to melt. Sea levels began to rise inexorably, and raging waters engulfed land bridges like Sunderland and Beringia. Coastlines were transformed beyond recognition, and new island states arose in the place of flooded plains. The vast mammoth steppe, which had supported countless herds, began to disappear, giving way to dense forests and new types of pastures. This ecological upheaval spelled doom for many Ice Age giants. Human societies in Asia were forced to adapt to these dramatic changes. It was this need to adapt, to seek new food sources, and to change their way of life that ultimately led to the greatest revolution in history, the emergence of agriculture. Across the continent, from the Fertile Crescent in West Asia to the rice paddies of East Asia, people began to master farming. The Asian Ice Age wasn't just a time of cold and survival. It was a harsh ordeal that pushed humanity to incredible adaptations, cultural breakthroughs, and great migrations that forever changed the demographic map of our planet. When we think of an ice age, our imagination conjures up images of vast ice sheets and herds of woolly mammoths. However, it's worth remembering that this picture is far from true for the entire planet. Africa, located primarily in tropical latitudes, was never bound by continental glaciers. Nevertheless, the last ice age, which raged from approximately 110,000 to 12,000 years ago, had a colossal impact on the climate, ecosystems, and the very history of the African continent. Africa's experience adapting to these changes, as well as its role as the cradle of modern humans, is key to understanding the history of our species. Glaciation on the Dark Continent was a localized phenomenon, limited to only the highest mountain ranges. Majestic peaks such as Kilimanjaro, Kenya, and the Ruwenzori Mountains in East Africa, as well as the Atlas Mountains in the north, were capped by mountain glaciers. During the coldest phases of the Ice Age, these glaciers were significantly larger than they are today. However, they remained isolated islands of ice, not coalescing into the gigantic ice sheets that covered Europe and North America. Yet, despite the lack of an ice cap, Africa experienced dramatic and widespread climatic upheavals. The main trend was not cooling, but desiccation. Conditions became increasingly arid, reaching their peak during the last glacial maximum, approximately 20,000 years ago. Cooler temperatures across the planet led to reduced evaporation from the oceans. This, in turn, meant that less moisture entered the atmosphere, and rainfall across much of the continent dropped sharply. Africa suffered from severe drought. Deserts, such as the Sahara and Kalahari, began to expand, encroaching on ever-increasing territory. They became far more vast and lifeless than we know them today, becoming insurmountable barriers to the movement of people and animals. Tropical forests in Central and West Africa also succumbed to the onslaught of aridity. They shrank, becoming small, isolated pockets of life, a kind of refuge where species could wait out unfavorable times. This shrinking forests and advancing deserts led to the fragmentation of ecosystems. Human and animal populations found themselves cut off from one another, leading to periods of isolation and independent development, as well as new contacts during temporary climate mitigations. Rainfall deficits have dealt a devastating blow to Africa's major lake and river systems. Imagine the water level in Lake Victoria, one of the world's greatest lakes, dropping drastically, at times completely reducing it to a few small bodies of water. Numerous small lakes and swamps have dried up completely. Even mighty rivers like the Nile have experienced dramatic changes in flow patterns and reduced water volumes. This hydrological stress has placed enormous pressure on all flora and fauna, forcing them to either adapt or migrate in search of more moisture and food. Of course, the picture wasn't entirely monochromatic. Some regions of Africa experienced brief increases in humidity during certain phases of the Ice Age. This occurred at the very beginning and end of glacial cycles or in areas influenced by changing atmospheric currents. However, the overall trend across most of the continent during glacial maxima was clear. It became cooler and significantly drier. Powerful winds, similar to those that blew in periglacial zones on other continents, further exacerbated the drought, raising clouds of dust into the air. These climate shifts had a profound impact on Africa's flora and fauna. As grasslands and savannas expanded in place of retreating forests, animal populations adapted to open spaces gained an advantage. Vast herds of herbivores such as wildebeest, zebras, and other ungulates thrived on the vast grasslands. At the same time, forest species faced catastrophic habitat loss. African megafauna, elephants, rhinoceroses, and hippos, though not requiring the dense fur of their northern counterparts, were also severely impacted by climate change. Their survival depended directly on constant access to water and abundant vegetation. It's important to remember that Africa was the cradle of humanity, and the Ice Age climate played a decisive role in the evolution of modern humans and their dispersal. Our species, Homo sapiens, emerged in Africa and adapted to its changing conditions long before it began its triumphant march across the planet. Periods of severe drought and habitat fragmentation likely served as the evolutionary driver that propelled human development and stimulated migrations across the African continent. The formation of small, isolated groups of people could have led to the development of unique local adaptations. And when conditions changed and these groups expanded their territories and re-emerged, an exchange of genes and cultural achievements occurred, enriching our species. The Great Migrations out of Africa, which led to human settlement across the entire planet, were directly influenced by the climatic cycles of the Ice Age. Temporary periods of wetter climate created so-called green corridors, allowing people to cross vast desert expanses to travel from Africa to the Middle East and further to Asia. These migration routes often followed coastlines or river valleys, which could provide sufficient water and resources for the long and dangerous journey across arid lands. The exact timing and routes of these migrations are still the subject of scientific debate. But one thing is clear: they were inextricably linked to favorable windows in the harsh climate of the Ice Age. Meanwhile, in Africa itself, people were not idle. They developed sophisticated stoneworking technologies, such as the Middle Stone Age industry, characterized by skillfully crafted spearheads, scrapers, and blades that were true masterpieces of their time. Ancient Africans developed diverse survival strategies, perfectly adapted to a variety of conditions, from coastal zones to savannas and forests. They learned to exploit all available resources, they gathered shellfish, fished, knew countless edible plants, and, of course, hunted wild animals. The discovery of the first signs of symbolic thought, such as personal jewelry, beads made from ostrich eggshells, and early forms of rock art, testify to the highly sophisticated cognitive abilities and rich culture that developed during that distant period. Thus, the Ice Age in Africa was not a time of stagnation, but an era of great challenges and great achievements.